There's an object out there, drifting through the darkness beyond Neptune's orbit right now, that's been called the single most dangerous object known to humanity. It's enormous, more than twice the size of the asteroid that ended the age of dinosaurs. If it hit Earth, the impact energy would exceed the dinosaur-killing event by a factor of 27. And it's heading back toward us. But here's what they don't tell you in the headlines. This cosmic behemoth is also responsible for one of the most beautiful sights you'll ever witness. Every August, when Earth passes through the trail of debris it left behind, the sky erupts with light. Not destruction, beauty. Dozens of meteors every hour, streaking across the darkness like brushstrokes of fire painted on velvet, the Perseids. And in 2025, despite this shower's dangerous parentage, you'll have a front row seat to watch fragments of this massive comet burn up safely, harmlessly, spectacularly, 80 kilometers above your head. This is just one of 3 cosmic stories that will unfold above you in 2025. In January, you'll witness meteors from an object that astronomers lost track of for over a century, a mysterious parent body that might be the dormant corpse of a comet that blazed across medieval skies. In December, you'll watch debris from a rocky asteroid that shouldn't even be able to create a meteor shower, yet somehow produces the most reliable celestial fireworks display of the entire year. The Quadrantids in January, the Perseids in August, the Geminids in December. 3 showers, 3 completely different origin stories, and each one will reveal something unexpected about the solar system we inhabit. But these showers are more than beautiful. They're evidence of something stranger. Each meteor you see burning overhead began its journey millions or even billions of years ago, forged in the cold outer reaches of the solar system, or the dense chaos of the asteroid belt. The debris streams we pass through are fossil rivers, trails of dust, and pebbles left by parent bodies that have orbited the sun for eons. Some of these particles have drifted through space longer than humans have walked the Earth. When they finally meet our atmosphere, they illuminate for just a fraction of a second, a brilliant farewell before they vanish forever. And yet, something peculiar is happening. One of these showers, the Geminids, wasn't even recorded until 1862. For all of human history before that, it simply didn't exist in our records. Now, it's the strongest, most reliable meteor shower of the year. This suggests the debris stream is young, perhaps only a few thousand years old. But here's the twist. Its parent body, asteroid Phaethon, should have shed this material over millions of years. So why did we only start seeing it 160 years ago? The answer points to processes happening right now. Streams still forming, the solar system still in motion, still changing in ways we're only beginning to understand. In 2025, the viewing conditions tell their own story. The Quadrantids will grace dark, moonless skies in early January, offering what could be the best view in years, though their peak lasts only a few precious hours. The Perseids, normally the crown jewel of summer meteor watching, will compete with a bright gibbous moon in August, a challenge that will teach us which meteors are bright enough to punch through moonlight. And the Geminids, often considered the year's most reliable shower, will peak under near-perfect conditions in mid-December, with a thin crescent moon that rises late and leaves the evening sky dark and clear. Throughout human history, meteor showers have inspired awe, fear, and sometimes terror. Ancient cultures saw them as omens, divine messages written across the heavens. Medieval observers called them falling stars, believing celestial bodies were literally plummeting to Earth. But nothing prepared the world for November 13th, 1833. That night, over North America, the sky erupted. Not dozens of meteors per hour, not hundreds, thousands. Some eyewitnesses estimated 100,000 meteors fell per hour, so many that people couldn't count them, couldn't even follow individual streaks anymore. The meteors came down like snowfall, like rain, filling the entire sky with light. Many believed the world was ending. Enslaved people in the American South saw it as a sign that liberation was coming. Others fell to their knees in prayer. Artists created illustrations showing meteors streaming from the sky so thickly they looked like cascading water. This was the Leonid meteor storm of 1833, and it changed astronomy forever. For the first time, scientists realized these displays weren't random. They returned on predictable schedules. They came from specific points in the sky, and most importantly, they could be studied, measured, understood. Within decades, astronomers connected meteor showers to comets, calculated debris stream orbits, and transformed what had been seen as supernatural phenomena into natural, explainable events. It wasn't until the 19th century, spurred by that terrifying night in 1833, that scientists truly began to understand what meteors were and why they appeared in predictable patterns each year. That understanding opened up entire new fields of study, revealing not just the mechanics of shooting stars, but the deep history of our solar system itself, written in trails of ancient dust. So welcome to the Sleepable Science channel. I'm so glad you found your way here, because tonight we're embarking on a journey through 2025's most breathtaking celestial displays. We'll explore the science behind each meteor shower, understand why some are brief while others linger for weeks, and discover what modern researchers are learning from these annual visitors. We'll trace the orbits of comets and asteroids, follow debris streams across millions of miles, and examine how tiny grains of cosmic dust transform into brilliant streaks of light. Whether you're planning to bundle up on a January night to catch the Quadrantids, spread a blanket under August stars for the Perseids, or close out the year watching December's Geminids, this exploration will deepen your appreciation for what you're witnessing. You'll learn when to look, where to direct your gaze, and what makes each shower unique. You'll discover why some meteors are slow and colorful, while others zip by in brilliant white flashes. And you'll understand why, despite the challenges of modern light pollution and busy schedules, meteor showers remain one of the most accessible and rewarding astronomical experiences available to anyone with clear skies and a sense of wonder. Before we dive into the specifics of each shower, I want to invite you to settle in. Let this be your moment to slow down, to let the concerns of the day drift away like morning mist. The universe operates on timescales far beyond our daily worries. Comets orbit for centuries. Asteroid streams persist for millennia. And the light from distant stars that you'll see tonight began its journey long before you were born. There's something deeply peaceful in that perspective, something that can help quiet a restless mind and ease you toward rest. If these calm cosmic explorations help you unwind, or if they give you a new way to appreciate the night sky, consider liking and subscribing to the channel. It helps others find their way here too, one curious soul at a time. Now, take a deep breath. Let your thoughts settle. And let's begin our gentle drift through the meteor showers of 2025, starting with the fundamental question: what exactly are we seeing when a meteor streaks across the sky? The science of shooting stars, understanding meteor showers. On a clear night, away from city lights, you might see 5 or 6 meteors in an hour. These are sporadic meteors, random bits of space debris encountering Earth's atmosphere. But during a meteor shower, that number can multiply tenfold or more. Dozens of meteors per hour, sometimes hundreds. And if you trace their paths backward across the sky, something remarkable emerges. They all seem to radiate from a single point, a specific location among the stars. This radiant point gives each meteor shower its name. The Perseids appear to emanate from Perseus, the Geminids from Gemini, the Quadrantids from a constellation that no longer exists, a region of sky. sky once mapped as quadrans muralis, but now absorbed into bodas. This radiant is not the source of the meteors themselves. It's an illusion of perspective, like looking down a long, straight road and watching the parallel edges appear to converge at a distant point on the horizon. The truth is more elegant. Every meteor in a shower is traveling along parallel paths through space. They move together, a vast river of debris orbiting the sun. When Earth's orbit intersects this stream, we plow through it like a car driving through rain. The parallel trajectories of the meteoroids, combined with our motion through the stream, create the illusion that they all emanate from a single point in the sky. It's geometry in action, the same principle that makes railroad tracks appear to meet in the distance. But what exactly are these objects? In space, they're called meteoroids. The term encompasses an enormous range of sizes, from particles no larger than grains of sand to chunks of rock the size of bowling balls. Most meteoroids in showers are tiny, barely larger than pebbles. A Perseid particle might measure a few millimeters across. A Geminid slightly larger. Their small size is precisely what makes them spectacular. When they encounter Earth's atmosphere at speeds ranging from 40,000 to 160,000 miles per hour, they don't have enough mass to survive. They burn up completely, transforming their kinetic energy into light and heat in a brilliant but brief display. The process begins at an altitude of about 75 to 120 kilometers, depending on the meteor's speed and angle of entry. At this height, the atmosphere is still quite thin, but not thin enough for objects moving at such tremendous velocities. As the meteoroid plows through the upper atmosphere, it compresses the air in front of it. This compression heats the air to extraordinary temperatures, thousands of degrees in an instant. The superheated air begins to glow, and more importantly, it begins to strip atoms from the meteoroid's surface. This process is called ablation. The meteoroid isn't really burning in the traditional sense. There's not enough oxygen at that altitude for combustion. Instead, the extreme heat is vaporizing the surface material, atom by atom, molecule by molecule. This vaporized material, along with the ionized air around it, creates the glowing trail we see. The meteor's brightness depends on several factors: its size, its speed, its composition, and the angle at which it enters the atmosphere. Fast meteors tend to be brighter. The Leonids, for instance, strike the atmosphere at roughly 71 kilometers per second, among the fastest of all meteor showers. This tremendous speed means more kinetic energy, more heating, and consequently more light. The Geminids, by contrast, are relative slowpokes at 35 kilometers per second. Still incredibly fast by any human standard, but about half the speed of the Leonids. This difference affects not only brightness, but also the duration of the streak. Slower meteors take slightly longer to traverse the sky, leaving trails that persist for a second or two rather than mere fractions of a second. Composition matters too. Different elements emit different colors when heated to plasma temperatures. Sodium produces yellow-orange light. Magnesium burns with a brilliant blue-green glow. Iron contributes whites and yellows. Calcium adds violets and purples to the spectrum. This is why experienced meteor watchers sometimes report that Perseids tend toward green, while Geminids often appear white or golden. These subtle color variations are spectroscopic signatures, chemical fingerprints that reveal what the meteoroid was made of. The angle of entry dramatically affects what we see. A meteoroid approaching the atmosphere nearly vertically will pierce straight down, creating a short, bright streak that appears and vanishes quickly. But a meteoroid arriving at a shallow angle, almost parallel to Earth's surface, will skim through the upper atmosphere for an extended period. These grazing entries produce what astronomers call Earth grazers, spectacular long-duration meteors that can traverse half the sky or more, leaving glowing trails that sometimes persist for several seconds after the meteor itself has vanished. Some meteors leave behind persistent trains, glowing trails that can linger for minutes. These aren't smoke or debris in the traditional sense. They're columns of ionized gas, atoms stripped of their electrons by the meteor's passage. These ions gradually recombine with electrons, releasing photons as they do so. The result is a faint, ghostly trail that slowly dissipates, twisted into strange shapes by upper atmospheric winds that blow at hundreds of kilometers per hour. The mathematics of meteor observation has its own elegant language. Astronomers use a measure called the zenithal hourly rate, or ZHR. This represents the number of meteors a single observer would see under perfect conditions. A perfectly dark sky, no light pollution, with the radiant directly overhead at the zenith. Real observing conditions almost never match this ideal. Light pollution reduces the number of visible meteors. A radiant low on the horizon means you're looking through more atmosphere, which dims fainter meteors. The presence of the moon can wash out all but the brightest meteors. This is why meteor shower predictions always include caveats. When astronomers say the Perseids have a ZHR of 100, they're not predicting you'll see 100 meteors per hour. Under typical suburban conditions with some light pollution, you might see 20 or 30. In bright moonlight, perhaps only 10 or 15. But in a truly dark location with the radiant high overhead, you might approach the theoretical maximum, watching meteor after meteor streak across an ink-black sky. The hourly rate also varies throughout the night and throughout the shower's active period. Most meteor showers have a peak, a period of maximum activity that can last anywhere from a few hours to a day or two. The Quadrantids have an unusually sharp peak, only about 6 hours of maximum activity. Miss that window, and rates drop dramatically. The Perseids, by contrast, maintain good activity for several days around their peak, giving observers multiple chances to catch the show. Timing within a single night matters too. Meteor showers are generally best observed after midnight, particularly in the hours before dawn. This isn't arbitrary. It relates to Earth's rotation and orbital motion as our planet orbits the sun. One hemisphere is always leading the way, facing forward into the direction of travel. That's the side experiencing morning. The other hemisphere is trailing, facing backward. The leading edge of Earth encounters more meteoroids, just as the front windshield of a car gets more raindrops than the rear window. This means the radiant point of most meteor showers rises higher in the sky as the night progresses, reaching its highest point around dawn. Higher radiant means more meteors visible and longer meteor trails as the meteoroids enter the atmosphere from a better angle. There are exceptions. Some minor showers have radiance that are highest in the evening. But for the major showers, including all three we're focusing on in 2025, the pre-dawn hours offer the best viewing, weather permitting. Meteor showers, unlike eclipses or transits, are forgiving events. Miss the peak by a day, and you'll still see meteors. Watch through thin clouds, and the brightest meteors will punch through. But there's no substitute for a clear, dark sky. Which brings us to one of the great challenges of modern meteor observation: light pollution. Artificial light has transformed the night sky over the past century. Where previous generations saw thousands of stars and could easily spot the Milky Way, many people today struggle to see more than a few dozen stars from their homes. This light pollution doesn't just dim stars, it washes out meteors too, rendering all but the brightest invisible. A meteor shower that would produce 60 visible meteors per hour in a dark location might yield only 10 or 15 from a suburban backyard, and perhaps just a handful from within a city. This is why meteor watching often requires effort, driving to a dark sky site, waiting for eyes to adjust, allowing time for the best viewing hours. But that effort pays dividends. Under truly dark skies, meteor showers transform from a pleasant curiosity into a profound experience. The sheer number of meteors, the visibility of fainter streaks, The backdrop of stars so thick they seem to blend together. All of this combines to create something that stays with you long after the night ends. The science of meteor showers extends far beyond simple observation. Researchers use sophisticated radar systems to detect meteors that occur during daylight hours or are too faint to see visually. Networks of cameras triangulate meteor paths, calculating precise trajectories and orbits. Spectroscopes analyze the light from bright meteors, revealing their chemical composition. All of this data feeds into our understanding of where these meteoroids came from, how old they are, and what they can tell us about the formation and evolution of the solar system. Because meteor showers aren't random, they're predictable, recurring phenomena tied directly to the orbits of specific parent bodies. Most showers originate from comets, those great wanderers of the outer solar system. A few, like the Geminids, come from asteroids. And as we'll discover in the following sections, each of the three major showers of 2025 has its own unique origin story, its own parent body drifting through the depths of space, slowly shedding the material that will one day light up Earth's skies. The Quadrantids, January's ephemeral wonder. The year begins with fire in the sky. While most of the world sleeps, bundled against winter's chill, the first major meteor shower of 2025 reaches its peak. The Quadrantids. They arrive in the cold, dark hours of early January. A brief but intense display that has earned a reputation as one of the most challenging showers to observe. Not because they're faint, quite the opposite. Under perfect conditions, the Quadrantids can produce over 100 meteors per hour, rivaling even the famous Perseids. The challenge lies in their timing. The Quadrantid peak is exceptionally narrow. While most meteor showers maintain maximum activity for 24 hours or more, the Quadrantids peak for only about 6 hours. Miss that window, even by half a day, and rates plummet. Watch too early, and you'll see only a few meteors. Watch too late, and the show is over. This brevity stems from the shower's orbital geometry. The debris stream is thin, and Earth crosses it at a nearly perpendicular angle, slicing through the densest region in just a few hours. In 2025, the predicted peak occurs between 1500 and 1800 Universal Time on January 3rd. For observers in North America, particularly those in Western time zones, this timing is nearly ideal. The peak activity window falls during the pre-dawn hours of January 3rd, when the radiant point is high in the northeastern sky, and the dark hours before sunrise offer perfect viewing conditions. Even better, the moon cooperates beautifully. A waxing crescent, only about 9% illuminated, sets during the evening hours, leaving the overnight period completely dark. This is exceptional luck. Meteor showers don't care about our calendar or convenience. The Quadrantids peak when they peak, determined by orbital mechanics that were set in motion thousands of years ago. Sometimes that peak coincides with a full moon. Sometimes it falls during daylight for most observers. But in 2025, for skywatchers in Alaska, Hawaii, and Western North America, the stars align literally and figuratively. Dark skies, favorable timing, and the Quadrantids' potential for high rates combine to create one of the year's best opportunities for meteor watching. The shower takes its name from a constellation that no longer exists. Quadrans Muralis, the Mural Quadrant, was a constellation created in 1795 by French astronomer Jérôme Lalande. It depicted a quadrant, an astronomical instrument used to measure the positions of stars. The constellation occupied a region of sky near the handle of the Big Dipper, between the modern constellations of Boötes and Draco. When the International Astronomical Union standardized constellation boundaries in 1922, Quadrans Muralis didn't make the cut. It was absorbed into Boötes, erased from official star charts. But the meteor shower named for that lost constellation remains. Some astronomers have suggested renaming it the Boötids, after the modern constellation that contains its radiant point. But tradition holds strong in astronomy, and the Quadrantids they remain, a living memorial to a defunct constellation. It's a reminder that our maps of the sky, like all maps, are human constructions, subject to revision and refinement. The stars themselves don't care what we call them. The radiant point lies at approximately right ascension, 15 hours 20 minutes. Declination 49 degrees north. For observers at mid-northern latitudes, this translates to a point in the northeastern sky that rises after midnight and reaches its highest point around dawn. This far northern radiant means the Quadrantids are primarily a northern hemisphere shower. Observers south of the equator see very little activity, as the radiant barely rises above their horizon. Quadrantid meteors themselves have distinctive characteristics. They tend to be bright, with many reaching fireball status. A fireball is any meteor brighter than Venus, capable of casting shadows and leaving after images that persist even after you close your eyes. The Quadrantids produce an above-average number of these brilliant meteors, adding drama to the display. They also tend to be blue-white in color, a signature of their high entry speed and specific composition. The speed is respectable, about 41 kilometers per second. Not as fast as the Leonids or Perseids, but still tremendously fast by earthly standards. At this velocity, a quadrantid meteoroid takes only about a second to cross the entire sky if it enters at a favorable angle. Most meteors appear and vanish in less time than it takes to register what you've seen. Brief flashes that leave you wondering if you actually saw something, or if your eyes played tricks on you in the darkness. The mystery of the Quadrantids extends beyond their fleeting peak. For many years, astronomers couldn't identify their parent body. Every major meteor shower is associated with a specific comet or asteroid, the object that shed the debris now orbiting the Sun. But the Quadrantids' parent remained unknown for over a century. The debris stream clearly existed. Its orbit was well determined. But no comet or asteroid with a matching orbit could be found. The breakthrough came in 2003, when astronomers at the Lowell Observatory discovered a small near-Earth asteroid and designated it 2003 EH1. Subsequent orbital calculations revealed something remarkable. This asteroid's orbit matched the Quadrantid stream almost perfectly. It was the missing parent body, hiding in plain sight. But 2003 EH1 is unusual. It's not a typical rocky asteroid. Its orbit is comet-like, highly elliptical, taking it from beyond Mars at its farthest point to well inside Earth's orbit at perihelion. This has led researchers to classify 2003 EH1 as a possible extinct comet or rock comet. The working hypothesis suggests that it may have once been an active comet, shedding gas and dust as it approached the Sun. Over many orbits, perhaps thousands of years, it could have exhausted its volatile ices, leaving behind the rocky core we see today, dormant and dark, no longer producing the characteristic tail and coma of an active comet. If this interpretation is correct, the Quadrantid meteoroid stream would represent debris left over from 2003 EH1's more active past, particles ejected thousands of years ago that now drift along its orbital path. There's even a tantalizing historical thread to pull. Some astronomers have noted intriguing similarities between 2003 EH1's orbit and that of a comet observed by Chinese and Korean astronomers in 1490, designated comet C1490Y1. The orbital elements are similar enough that calculations suggest they could potentially be the same object, or possibly related fragments from a larger parent body that broke apart centuries ago. If this connection proves valid, it would mean observers in 1490 witnessed the ancestor of today's quadrantid parent body during what may have been its final display of cometary activity before falling dormant. Another possibility adds even more complexity. Some meteoroid stream models indicate that Comet 96P Mach-Holtz might contribute to a broader, lower activity component of the Quadrantid stream, producing meteors outside the sharp peak. The evidence here is less definitive, but it raises an interesting prospect. The Quadrantid complex might be more intricate than a simple single-parent scenario, potentially incorporating debris from multiple related objects that share similar orbital characteristics. This complexity is common in meteor astronomy. What we call a single shower might actually be multiple streams, debris from different ejection events, or even different parent bodies, overlapping in space. Over time, gravitational perturbations from planets, particularly Jupiter, can alter the orbits of meteoroid streams, spreading them out, concentrating them, or even causing different parts of the stream to evolve along divergent paths. The Quadrantids we see today are the result of processes that played out over millennia, shaped by gravitational forces we're only beginning to fully understand. Observing the Quadrantids requires preparation. January nights are cold across much of the northern hemisphere, often brutally so. Warm clothing is essential. Not just a jacket, but layers, thermal underwear, insulated boots, gloves that are warm but still allow you to operate cameras or binoculars, a warm sleeping bag or heavy blanket, hot drinks in a thermos. The cold is the real enemy during January meteor watching, far more so than clouds or light pollution. But if you can manage the cold, if you can find a dark site and position yourself with a clear view of the northeastern sky, the reward can be extraordinary. Picture this. It's 4:00 a.m. on January 3rd, 2025. You're lying on a reclining chair or blanket, face turned toward Perseids and the Big Dipper. The sky is crystal clear, winter cold having scrubbed away any haze. Your eyes have adjusted, and you can see thousands of stars, more than you remember ever seeing before. Then a meteor, a bright streak, bluish white, crossing from northeast to southwest in less than a second. Then another, fainter, near the horizon. Then two more in quick succession, one leaving a glowing train that persists for 3 or 4 seconds before fading. You're not counting anymore. You're simply watching, mesmerized, as the universe puts on a show that's been playing for thousands of years and will continue for thousands more. The Quadrantids have been observed since at least 1825, though the shower probably occurred for centuries before anyone thought to record it systematically. Early records describe intense displays, sometimes with rates exceeding 100 per hour. These observations helped establish the Quadrantids as one of the major annual showers, despite their brief peak and winter timing. Modern meteor photography and radar observations have confirmed what early visual observers reported. During the peak hours, the Quadrantids can produce spectacular displays, but they're also variable. Some years produce strong displays with high rates. Other years are more modest. This variability likely relates to the structure of the debris stream and how precisely Earth's orbit intersects it. The densest parts of the stream may be clumped or uneven, so subtle differences in timing or geometry can significantly affect what observers see. This unpredictability adds an element of uncertainty to Quadrantid watching. You might see 100 meteors per hour. You might see 40. The only way to know is to go outside and look. For observers who cannot catch the narrow peak, there's still hope. The Quadrantids are active from late December through mid-January, producing a low background rate of meteors, even away from maximum. These off-peak Quadrantids are fewer, but they still originate from the same radiant and carry the same characteristics. If you miss the peak window on January 3rd, watching on January 2nd or 4th will still yield some meteors, just at lower rates. Radio observers have an advantage with the Quadrantids. Radio meteor detection works by picking up reflections from the ionized trails that meteors leave behind. This technique works day or night through clouds or clear skies. For the Quadrantids, this means radio observations can track activity throughout the daylight peak for observers in Europe and Asia, regions where the January 3rd maximum occurs during afternoon hours when visual observation is impossible. The scientific value of the Quadrantids extends beyond the beauty of the display. Each observed meteor provides data. Its brightness, duration, and trajectory all offer clues about the meteoroid that produced it. Analyzing hundreds or thousands of quadrantid meteors helps researchers understand the structure and age of the debris stream, the composition of the parent body, and the processes that created the stream in the first place. As 2025 begins, the Quadrantids offer an early reminder that the universe doesn't rest, even in the cold depths of winter. While the Earth sleeps through its longest nights, the cosmos continues its ancient dances. Asteroids orbit. Debris streams drift. And when our planet's path intersects these rivers of dust and pebbles, the sky comes alive with light, a New Year's celebration written in fire across the heavens. The Perseids, summer's celestial rivers of light. August brings warmth and the Perseids. For many people in the Northern Hemisphere, this is their first and perhaps only encounter with meteor showers. The timing is perfect. Summer vacation, warm nights, no need for heavy coats or sleeping bags. You can simply lie on a blanket in the backyard, look up, and watch the stars fall. The Perseids have been called the best meteor shower of the year, and for good reason. They're reliable, active, and occur when weather and temperature make outdoor observation comfortable rather than an exercise in endurance. In 2025, the Perseids face a significant challenge: the moon. The peak is predicted for the night of August 12th, 13th, with maximum activity occurring around 017 to 081 Universal Time on August 13th. For most of North America, this translates to the pre-dawn hours of August 13th, normally ideal timing. But the moon has other plans. It reaches its full phase on August 9th, just 3 days before the Perseid peak. By the night of August 12th to 13th, the moon is a waning gibbous, still 84% illuminated, brilliant and high in the sky during the prime meteor watching hours. This changes everything. Under dark, moonless skies, the Perseids can produce 100 meteors per hour or more. In 2025, with bright moonlight washing across the sky, expect rates to drop to perhaps 20 or 30 meteors per hour, maybe fewer depending on your location. The moon won't eliminate the shower, but it will hide the fainter meteors, leaving only the brightest visible. This is actually an interesting challenge for observers. You'll be hunting for fireballs, the spectacular bright meteors that can outshine even the moon. The strategy for 2025 involves positioning. If possible, place the moon behind an obstacle, a building, a hill, a stand of trees. Anything that blocks the moon's direct light will help. Face away from the moon, looking toward the darker parts of the sky. Your eyes will adapt better, and you'll catch more meteors. The early evening hours, before the moon rises, offer a brief window of darker skies, though rates are lower that early. And if you have the flexibility, consider observing a day or two before the peak, on the nights of August 10 to 11 or August 11 to 12, when rates are still good, but the moon is slightly less full and sets a bit earlier. Or wait until later in the month. The Perseids remain active from mid-July through late August, maintaining decent activity for several days on either side of the peak. By August 16 to 17, the moon will be in its last quarter phase, rising around midnight and leaving the evening hours darker. Rates will be lower than at peak, but the improved sky conditions might actually result in more visible meteors. This is one of the beauties of the Perseids. Their extended activity period offers multiple opportunities. The Perseids owe their existence to Comet Swift-Tuttle, one of the largest objects in the solar system to regularly cross Earth's orbit. This behemoth has a nucleus roughly 26 kilometers across, more than twice the size of the asteroid believed to have ended the age of dinosaurs. Every 133 years, Swift-Tuttle completes an orbit that takes it from beyond Neptune's orbit at its farthest point to well inside Earth's orbit at perihelion. It last returned in 1992, when it was recovered by Japanese amateur astronomer Tsuruhiko Kyuchi after more than a century away from the inner solar system. The comet was first discovered in July 1862, independently by two observers. Lewis Swift found it on July 16th, using a telescope at his private observatory in Marathon, New York. 3 days later, on July 19th, Horace Parnell Tuttle spotted the same comet from Harvard College Observatory. Both men were accomplished comet hunters, and both immediately recognized they'd found something significant. The comet was bright enough to be seen through small telescopes and even binoculars as a fuzzy patch with a faint tail. Thus, the double-barreled name, Swift-Tuttle, honoring both independent discoverers. This was common practice in the 19th century, before modern systematic sky surveys made independent discoveries rare. Neither Swift nor Tuttle realized at the time that they'd found the source of the Perseids, that ancient meteor shower that had been observed for centuries. That connection came later, made by Italian astronomer Giovanni Schiaparelli in 1866. Schiaparelli was studying meteor shower radiance, trying to determine the precise points in the sky from which different showers appeared to emanate. When he calculated the orbit of the Perseid meteor stream, based on observations from multiple years, he recognized something remarkable. The orbit matched the newly determined orbit of Comet Swift-Tuttle almost perfectly. Same inclination, same eccentricity, same perihelion distance. The match was too close to be coincidence. This was revolutionary. It confirmed the connection between comets and meteor showers, a hypothesis that had been proposed but not proven. Schiaparelli's work demonstrated that meteor showers weren't atmospheric phenomena, as some scientists still believed, but rather the result of Earth passing through trails of debris left behind by comets. It established a framework, a myth, for understanding all meteor showers as the intersection of Earth's orbit with the orbital paths of their parent bodies. And it meant that wherever Comet Swift-Tuttle went, whenever it passed through the inner solar system, it left behind material that would eventually produce meteors when Earth plowed through it. The comet disappeared from view after 1862, heading back to the outer solar system on its 133-year orbit. Astronomers calculated when it should return, sometime around 1992. But comets are notoriously difficult to predict. Their orbits change slightly with each passage due to non-gravitational forces, the rocket effect of jetting gas pushing on the nucleus in unpredictable ways. When 1992 arrived, searches began, but the comet was nowhere to be found. Had it disintegrated? Changed its orbit dramatically? Broken into pieces? Then, on September 26, 1992, Japanese amateur astronomer Tsuruhiko Kyuchi made a discovery that electrified the astronomical community. Using 25 by 150 binoculars from his observing site, he spotted a comet in the constellation Lacerta. Confirmation came quickly. This was Swift-Tuttle, back after 130 years. But there was a problem. The comet arrived 17 days later than predicted. That 17-day difference set off alarm bells. If Swift-Tuttle was 17 days late this time, and if that delay accumulated or worsened with each orbit, then by its next return in 2126, it might arrive at a catastrophically different time. Some quick calculations suggested a disturbing possibility. If the comet arrived just 15 more days late in 2126, it would pass through the exact point in space where Earth would be on August 14th of that year. The implications were staggering. With a nucleus 26 kilometers across, Swift-Tuttle isn't just large, it's enormous, more than twice the size of the asteroid that ended the age of dinosaurs 66 million years ago. An impact would release energy equivalent to 27 times that extinction-level event. As Brian Marsden at the Harvard Smithsonian Center for Astrophysics put it, Swift-Tuttle had become the single most dangerous object known to humanity. The astronomical community mobilized. Telescopes worldwide tracked the comet, refining its orbit with each observation. But the real breakthrough came from an unlikely source: ancient history. Amateur astronomer and comet expert Gary Kronk began searching through historical records, looking for any mentions of comets that might match Swift-Tuttle's orbit. He found two crucial observations: a comet seen by Chinese astronomers in 69 BCE and another in 188 CE. When Brian Marsden calculated the orbits of these ancient sightings, they matched Swift-Tuttle's orbit remarkably well. These were almost certainly earlier returns of the same comet, which meant astronomers now had observations spanning over 2,000 years instead of just 130. With these additional data points, the orbit could be determined far more precisely. The refined calculations brought relief. While Swift-Tuttle does pass close to Earth's orbit, the timing won't align for a collision in 2126. The comet will pass safely, missing Earth by a comfortable margin. Later encounters in 3044 and 4479 will be closer, but modeling suggests those two will be near misses rather than impacts. The long-term probability of a collision remains non-zero, but for at least the next several thousand years, we appear to be safe. What's remarkable is how close we came to not knowing. Without those ancient Chinese observations, without Kronk's diligent historical research, the uncertainty would have remained. We would have spent 134 years wondering if Swift-Tuttle might end civilization on its next return. Instead, we know the truth. This massive, potentially devastating comet will continue to grace our skies harmlessly, shedding the beautiful Perseid meteors that light up August nights. The 1992 return of Swift-Tuttle had another effect. It strengthened the Perseid meteor shower. In 1991, 1992, and 1993, observers reported enhanced Perseid rates, sometimes exceeding 200 meteors per hour. This makes sense. When the comet passed through the inner solar system, it shed fresh material, creating a denser filament in the debris stream. When Earth encountered that filament in subsequent years, the result was enhanced meteor activity. These periodic enhancements, tied to the parent comet's recent passage, demonstrate the dynamic nature of meteor streams. This was a revolutionary discovery. It confirmed that meteor showers weren't atmospheric phenomena, as some had believed, but rather the result of Earth passing through trails of debris left behind by comets. It established a framework for understanding all meteor showers as the intersection of Earth's orbit with the orbital paths of their parent bodies. And it meant that wherever Comet Swift-Tuttle went, whenever it passed through the inner solar system, it left behind material that would eventually produce meteors when Earth plowed through it. Swift-Tuttle is a Halley-type comet, defined as having an orbital period between 20 and 100 years. Its 133-year period puts it squarely in this category. The comet follows a steeply inclined orbit, tilted at a considerable angle to the plane of the solar system. This means that when Earth encounters the Perseid stream, the meteoroids are striking our atmosphere almost head-on, approaching from nearly the opposite direction of Earth's motion around the Sun. This head-on collision produces tremendous relative velocities. Perseid meteors enter the atmosphere at about 60 kilometers per second, among the faster meteor showers. This speed contributes to the Perseids' brilliance. Faster meteors mean more kinetic energy, more heating, and consequently more light. Perseids are often bright, with many reaching magnitude 0 or brighter, as luminous as the brightest stars. They also frequently produce persistent trains, those ghostly glowing trails that can linger for several seconds after the meteor itself has vanished. These trains form when the meteor's passage ionizes the atmospheric gases, creating a column of glowing plasma that slowly recombines and fades. The Perseid meteoroids themselves are thought to be primarily dust and small pebbles, fragments of ice and rock that boiled off Swift-Tuttle's nucleus during its many passages through the inner solar system. Some of this debris is ancient, ejected thousands of years ago. Other material is more recent, shed during the comet's 19th and 20th century returns. The debris doesn't spread uniformly along the orbit. Instead, it forms filaments and clumps, denser regions that can produce brief bursts of enhanced activity when Earth passes through them. Historical records of the Perseids stretch back nearly 2 millennia. Chinese manuscripts from 36 CE describe a meteor shower occurring in midsummer, almost certainly the Perseids. Japanese and Korean astronomers also recorded this shower in subsequent centuries. European records become more detailed, starting in the Middle Ages. In some Catholic traditions, Perseid meteors are known as the Tears of St. Lawrence, after the Christian martyr executed on August 10th in the year 258. The shower's peak, falling just days after the saint's feast day, was seen as divine commemoration. The reliability of the Perseids has made them a favorite among both amateur and professional astronomers. Year after year, the shower delivers. There are variations, of course. Years when the comet passed nearby produce enhanced displays with rates sometimes exceeding 200 per hour. The 1990s, when Swift-Tuttle returned, saw several spectacular Perseid outbursts. But even in normal years, the Perseids rarely disappoint, maintaining consistent rates that justify their reputation as one of the best annual showers. One of the Perseids' most appealing characteristics is their timing. August nights are comfortable across much of the northern hemisphere. No need for extreme cold weather gear. In many locations, you can simply step outside in shorts and a t-shirt. This accessibility brings meteor watching to people who might never bundle up for January Quadrantids. School-aged children on summer vacation can stay up late or rise early to watch. Families can make it an event, spreading blankets in the yard or driving to a nearby dark site. The radiant point in Perseus rises in the northeast during the evening hours and climbs steadily through the night, reaching its highest point just before dawn. This means Perseid meteors can be seen all night long, though rates increase as the radiant climbs higher. Early evening, before the radiant has risen very high, is prime time for Earth grazers, those spectacular, long-duration meteors that skim through the upper atmosphere at shallow angles, sometimes traversing half the sky before burning up. Earth grazers are special. They're rare but memorable. Imagine watching the northern sky just after sunset, when the first stars are appearing, but the sky still holds some twilight glow. Suddenly, a meteor appears low on the horizon, moving slowly compared to typical meteors. It glides across the sky, bright and purposeful, leaving a glowing train behind it. The whole event might last 2 or 3 seconds, an eternity in meteor terms. You can actually follow its progress, watch it traverse constellation after constellation, before finally fading near the opposite horizon. These Earth grazers occur when a meteoroid approaches Earth from a direction parallel to the horizon. Instead of diving steeply into the atmosphere, it skims through the upper layers at a shallow angle. This extended path through the atmosphere means the meteoroid takes longer to ablate, producing a longer-lasting display. Because they occur when the radiant is near the horizon, Earth grazers are most common in the early evening, before the radiant has climbed high. As the night progresses and the radiant rises, meteor rates increase, but the meteors themselves become shorter and faster. By 3 o'clock or 4 a.m., when the radiant is high overhead, you're looking directly into the stream, encountering meteoroids head-on. These meteors appear all over the sky, radiating out from Perseus in all directions. Some are bright, others are faint, barely visible even under dark skies. But together, they create a sense of cosmic activity. A reminder that space isn't empty, but filled with ancient debris, silent travelers orbiting the sun for eons. The Perseids have colors, subtle but distinct if you know what to look for. Many appear white or yellow, the color of superheated air, but others show hints of green, the signature of magnesium burning in the meteor's trail. A few flash orange or red, likely from sodium or calcium. These colors are fleeting, gone almost before you register them. But they're real, spectroscopic evidence of the meteoroid's composition. Photographers love the Perseids. The combination of warm weather, reliable activity, and relatively bright meteors makes them ideal subjects for long exposure astrophotography. Point your camera at the sky, set it for a 20 or 30 second exposure, and let it run. Over the course of several hours, you'll capture multiple meteors, their trails imprinted on the image like calligraphy written in light. Composite these images together, and you can create stunning visualizations of the shower, dozens of meteors radiating from Perseids, each one a fragment of Comet Swift-Tuttle burning up in Earth's atmosphere. Modern meteor science benefits enormously from the Perseids. The shower's reliability means researchers can plan campaigns well in advance, deploying instruments and coordinating observations. Networks of video cameras capture thousands of Perseid meteors each year, triangulating their paths to determine precise trajectories and calculate orbits. Spectroscopes analyze the light from bright Perseids, revealing detailed chemical compositions. Radio. Observations track meteor activity even during daylight hours. All this data feeds into models of the Perseid stream's structure and evolution. By understanding how the stream is distributed in space, how dense it is in different regions, researchers can work backward to infer when and how Swift-Tuttle shed this material. They can also predict future Perseid displays, identifying years when Earth might pass through denser filaments and produce outburst activity. And they gain insights into the broader processes of how comets lose mass, how debris streams form and evolve, and how these streams interact with planetary gravity over time. The 2025 Perseids won't be the easiest to observe, given the moon's interference, but they'll still be worth the effort. Even reduced rates of 20 or 30 meteors per hour translate to a meteor every few minutes, enough to maintain interest and provide a sense of the shower's activity. And the meteors that do appear will be the brightest, the fireballs that can punch through moonlight and leave lasting impressions. For those unable to observe in person, numerous online platforms stream live footage during the Perseids' peak. Cameras at dark sky sites broadcast all night, capturing meteors and sharing them with global audiences. It's not the same as lying under the stars yourself, feeling the cool night air and watching meteors with your own eyes. But it's something, a way to participate in this annual celestial event, even if weather, location, or circumstance keeps you indoors. As August 2025 unfolds and the Perseids reach their peak, remember that you're witnessing something ancient. Those meteors aren't random sparkles, but fragments of Comet Swift-Tuttle, a massive icy body that has orbited the Sun for millions of years. Every Perseid you see represents a tiny piece of that comet, shed decades or centuries ago, finally reaching the end of its journey in a brief blaze of glory high above your head. The comet itself is out there somewhere, far beyond the orbit of Neptune, silently tracing its elliptical path through the outer solar system. It won't return until 2126, more than a century from now. But its legacy remains, scattered along its orbital path, waiting for Earth to pass through and light the August sky with fire. The Geminids, December's golden finale. December brings cold and the year's final major meteor shower. The Geminids arrive during the darkest month, when nights stretch long and winter settles across the northern hemisphere. But unlike the Quadrantids, which require observers to brave frigid pre-dawn hours, the Geminids offer a more convenient viewing schedule. Their radiant rises in the early evening, climbs through the night, and reaches its highest point around 2 o'clock a.m. This means you can start watching soon after sunset, when the radiant is still low but rising, and catch meteors throughout the evening and night. For many astronomers, the Geminids are the year's best meteor shower. Not the most famous. That honor goes to the Perseids. Not the fastest. The Leonids claim that distinction. But the most reliable. the most consistent, and in terms of sheer numbers, often the most productive. In a typical year under dark skies, the Geminids can produce 120 meteors per hour or more at their peak, sometimes approaching 150. They maintain high rates for more than a day, giving observers multiple opportunities. And they're known for producing bright meteors, fireballs that light up the sky and leave colorful trails. In 2025, conditions are excellent. The peak occurs on the night of December 13th to 14th, with maximum activity predicted around 03 unclock Universal Time on December 14th. For observers in the Americas, this translates to the evening of December 13th into the early morning hours of December 14th. The moon is a waning crescent, only about 30% illuminated, rising around 2 o'clock a.m. This means the entire evening is moonless, offering dark skies during prime viewing hours. By the time the moon does rise, the Geminids are still going strong, and the moon's thin crescent won't significantly interfere. This is about as good as conditions get for a major meteor shower. No bright moon, favorable timing, and the Geminids' inherent reliability. If weather permits, if clouds don't interfere, December 13th to 14th, 2025 could provide one of the year's most spectacular meteor displays for observers across North America, Europe, and much of Asia. The Geminids take their name from Gemini, the constellation containing their radiant point. Gemini is easy to find in December, high in the eastern sky during evening hours. The two brightest stars, Castor and Pollux, mark the heads of the celestial twins. The Geminid radiant lies near Castor, the northern of the two bright stars. When you see a meteor during the Geminids, you can trace its path backward, and it will appear to come from this region of sky. But unlike most meteor showers, the Geminids don't come from a comet. Their parent body is an asteroid, designated 3200 Phaethon. This makes the Geminids unusual, almost paradoxical. Asteroids are rocky bodies, lacking the volatile ices that cause comets to shed dust and gas when they approach the sun. Asteroids are supposed to be stable, inert, unchanging. So how does an asteroid produce one of the most prolific meteor showers in existence? The answer lies in Phaethon's orbit, which is anything but typical. This small asteroid, only about 5 kilometers across, ventures out past the orbit of Mars, then plunges sunward on a trajectory that takes it inside Mercury's orbit, passing just 0.14 AU from the Sun's surface, a mere 21 million kilometers. That's close enough that the name Phaethon, after the Greek mythological figure who drove the sun god's chariot too close to the sun, is disturbingly appropriate. At this proximity, something remarkable happens. Surface temperatures on Phaethon soar to around 730 degrees Celsius, hot enough to melt lead, hot enough to cause rocks to crack and fracture from thermal stress alone. Certain minerals and metals begin to vaporize. Volatile compounds trapped in the rock turn to gas, creating pressure from within. The result is a slow but steady release of dust and small fragments, a process different from normal cometary sublimation, but producing similar results: a debris stream scattered along the asteroid's orbit. Recent observations have detected a faint dust tail extending from Phaethon during its closest approaches to the Sun. This tail is incredibly weak compared to cometary tails, barely visible even with sophisticated instruments, but its existence confirms that Phaethon is still active, still shedding material, slowly contributing to the Geminid stream even now. Each time the asteroid passes perihelion, thermal fracturing releases more dust and tiny pebbles, adding to the debris scattered along its orbit. But here's where the story takes an unexpected turn. The Geminids weren't always a major shower. Historical records are strangely silent about this display until the mid-1800s. The shower was first clearly recorded in 1862, when observers noted unusual meteor activity from Gemini in December. For all of human history before that, for thousands of years of watching the skies, nobody recorded this shower. It simply wasn't there, or at least it wasn't noticeable. Over subsequent decades, the shower intensified, growing stronger with each passing year. By the early 20th century, the Geminids were recognized as a major annual shower, and they've continued to strengthen. Modern observed rates often exceed what early 20th century astronomers reported. The Geminids aren't just active, they're growing, intensifying, becoming more prominent with each orbit of their parent body. Why weren't they visible before 1862? This question has puzzled astronomers for decades. One leading hypothesis suggests the debris stream is relatively young, perhaps only a few thousand years old, and Earth's orbit has only recently begun intersecting the densest parts of it. Another interpretation points to gradual gravitational perturbations from Jupiter and Saturn, which over centuries could have shifted the stream's orbit, bringing it into progressively better alignment with Earth's path. But there's a third possibility, one that raises fascinating implications. What if Phaethon itself has changed? What if something about its perihelion passages has become more violent, more active in recent centuries? Evidence from observations suggests that thermal fracturing isn't constant. It can vary depending on the asteroid's rotation, surface composition, and internal structure. If Phaethon experienced some kind of structural change, perhaps a surface layer peeling away to expose fresh material, or internal cracks expanding from repeated thermal stress, it could be shedding material more rapidly now than it did centuries ago. This would mean Phaethon is in the midst of an accelerated disintegration phase. The asteroid we see today might be fundamentally different from the one that existed 1,000 years ago, steadily cracking apart under the relentless thermal punishment of its close solar passes. If so, the Geminids' intensification isn't just observational bias or orbital evolution. It's evidence of an asteroid breaking down in real time, accelerating its own demise with each orbit. Whatever the cause, the implication remains startling. We're witnessing something dynamic, a meteor shower not just existing, but actively forming and intensifying. The Geminids we see today are likely stronger than what ancient Romans or medieval astronomers would have seen had they paid attention to December skies. And they may be stronger than what our great-great-grandchildren will see. We're watching cosmic evolution unfold on human timescales, a reminder that eternal celestial phenomena are actually works in progress. The asteroid was discovered on October 11, 1983, by the Infrared Astronomical Satellite, IRAS. Initially designated 1983 TB, it received the name Phaethon in 1985, after the character in Greek mythology who drove the sun god Helios' chariot. The name is fitting. Just as mythological Phaethon ventured too close to the sun with disastrous results, asteroid Phaethon's orbit brings it perilously close to our star, subjecting it to temperatures that few solar system bodies experience. The connection between Phaethon and the Geminids was established by Fred Whipple, the legendary comet researcher who proposed the dirty snowball model of cometary nuclei. When Phaethon's orbit was calculated, Whipple realized it matched the Geminid stream almost perfectly. This was groundbreaking. It was the first time an asteroid had been definitively linked to a meteor shower, overturning the assumption that all meteor showers came from comets. Since that discovery, researchers have studied Phaethon intensively. Radar observations reveal a dark surface with very low albedo, reflecting only about 11% of the light that hits it. Spectroscopic analysis suggests a composition similar to carbonaceous chondrite meteorites, primitive, rocky material that hasn't been extensively processed by heat or melting. This supports the idea that Phaethon might be the remnant core of a larger body that lost its volatile outer layers over time. Recent observations have detected a faint dust tail extending from Phaethon during its closest approaches to the Sun. This tail is incredibly weak compared to cometary tails, but its existence confirms that Phaethon is still shedding material, slowly contributing to the Geminid stream. Each time the asteroid passes perihelion, thermal fracturing releases more dust and tiny pebbles, adding to the debris scattered along its orbit. The Geminid debris stream has been building for a long time, possibly thousands of years. But interestingly, historical records of the Geminids only go back to the mid-1800s. The shower was first clearly recorded in 1862, when observers noted unusual meteor activity from Gemini in December. Over subsequent decades, the shower intensified, growing stronger with each passing year. By the early 20th century, the Geminids were recognized as a major annual shower, and they've continued to grow, with modern observed rates exceeding what early 20th century astronomers reported. Why the increase? Astronomers aren't entirely sure, but one hypothesis involves orbital evolution. Over time, gravitational perturbations from planets can shift the Geminid stream's orbit, changing how it intersects Earth's path. If the stream has been gradually moving into a more favorable geometry, that could explain the observed strengthening of the shower. Alternatively, Phaethon might be shedding material more rapidly in recent centuries, perhaps due to some change in its surface or rotation. Whatever the cause, the result is clear. The Geminids are now one of the most prolific meteor showers, often producing higher rates than even the Perseids, and they show no signs of weakening. If anything, they continue to improve, year after year, a gradual intensification that suggests Earth is encountering denser regions of the stream. Geminid meteors have distinctive characteristics. They're relatively slow compared to showers like the Perseids or Leonids. Geminid meteoroids enter the atmosphere at about 35 kilometers per second, roughly half the speed of Perseid meteors. This slower entry speed means longer-lasting trails. A Geminid meteor might be visible for a full second or even two, giving you time to really see it, to register its motion and color before it vanishes. And Geminids are colorful, more so than most meteor showers. Many appear white or yellow, but others show distinct hues: greens, blues, oranges, even occasional purples. These colors come from the meteoroid's composition. Geminids seem to be rich in sodium, which produces yellow-orange emissions. They also contain magnesium, calcium, and iron, each contributing its own spectral signature. The result is a meteor shower that offers not just quantity, but quality, with bright, slow, colorful meteors that make excellent photographic subjects. The radiant point's evening visibility means the Geminids are convenient for casual observers. You don't need to stay up until 3 a.m. or wake before dawn. Starting around 9 or 10 p.m., once the radiant has climbed above the horizon, you can begin watching. Rates won't be at their maximum that early, but you'll still see meteors, and the ones you do see might be Earth-grazers. Those special, long-duration meteors that skim through the upper atmosphere when the radiant is low. As midnight approaches and passes, rates increase. By 2 a.m., when the radiant is nearly overhead, the Geminids are at their peak. If you're under dark skies, you might see a meteor every minute or two, sometimes more. They appear all over the sky, radiating from Gemini, but visible in any direction. The experience is mesmerizing. You lie back, eyes slowly scanning the heavens, and every few minutes a meteor streaks by. Sometimes bright, sometimes faint, sometimes leaving a trail, sometimes vanishing instantly. Each one unique, each one a tiny fragment of asteroid Phaethon, ending its long journey through space. The Geminids' December timing presents challenges, mainly related to weather and cold. December is often cloudy across many regions. Winter storms can obscure the sky for days. Even when clear, the cold is formidable. Temperatures well below freezing are common in northern latitudes, and even at mid-latitudes, December nights can be brutally cold. Proper preparation is essential. Dress in layers. Bring a warm sleeping bag or heavy blankets. Hot drinks. Waterproof ground cover if there's snow or wet grass. But that cold also has benefits. Cold air tends to be clearer, scrubbed clean by the passage of weather systems. Winter nights often have exceptional transparency, allowing you to see fainter stars and meteors than you could in summer's hazy warmth. If you can manage the discomfort, winter meteor watching rewards you with some of the clearest, darkest skies of the year. The Geminids are visible from both hemispheres, though northern hemisphere observers have a distinct advantage. The radiance declination places it high in the sky for northern latitudes, but lower for southern observers. Still, the shower can be seen from anywhere on Earth where Gemini rises above the horizon. Southern hemisphere observers won't see peak rates, but they'll still see Geminids, especially in the hours around local midnight when the radiant is highest for their location. Japan plans to visit Phaethon. In 2028, if all goes according to plan, JAXA, the Japan Aerospace Exploration Agency, will launch the Destiny Plus mission, a spacecraft designed to fly past Phaethon and study it up close. The encounter will be brief, a fast flyby rather than an orbital mission. But during that brief encounter, instruments will photograph Phaethon's surface, analyze its composition, and potentially detect the dust clouds surrounding it during perihelion passage. This mission will answer fundamental questions about Phaethon and the Geminids. Is Phaethon truly an asteroid, or is it an extinct comet core? How much material is it still shedding? What is the exact mechanism that produces the Geminid stream? The answers will revolutionize our understanding not just of one asteroid and its meteor shower, but of the broader processes that create and maintain meteoroid streams throughout the solar system. For observers in 2025, the Destiny Plus mission is still years away, but the knowledge that scientists are taking Phaethon seriously enough to send a spacecraft adds an extra layer of significance to watching the Geminids. You're not just seeing pretty lights in the sky, you're witnessing the ongoing disintegration of a solar system body, watching in real time as an asteroid slowly sheds its substance into space. Every Geminid meteor represents a piece of Phaethon, released years or decades ago, finally reaching Earth and burning up in our atmosphere. The Geminids close out the major meteor showers of 2025 with style. After them, only the minor Perseids remain, a small shower active around the winter solstice. Then the calendar rolls over, and the cycle begins again, with January's Quadrantids. This annual rhythm, the predictable return of familiar meteor showers, provides a kind of cosmic comfort. No matter what changes in the world, no matter what challenges arise, the meteor showers return. Earth passes through the same debris streams, year after year, century after century, and the sky fills with light. Cosmic origins, understanding parent bodies and debris streams. Every meteor shower has a source, a parent body that shed the material now burning up in Earth's atmosphere. For most showers, these parents are comets, those ancient icy wanderers of the outer solar system. A few, like the Geminids, come from asteroids. But whether the source is icy or rocky, the process that creates a meteor shower follows similar principles, governed by orbital mechanics and the gradual dispersal of debris across millions of kilometers. Comets are time capsules from the solar system's formation. They're composed of ice, dust, and rocky material, frozen together in what's often called a dirty snowball. Most comets orbit in the distant reaches of the solar system, far from the sun's warmth, in regions like the Kuiper Belt beyond Neptune, or the even more distant Oort cloud. In these cold zones, comets can remain frozen and dormant for millions of years, barely changed from their formation 4.6 billion years ago. But sometimes, gravitational perturbations nudge a comet's orbit, sending it plunging toward the inner solar system. As it approaches the sun, temperatures rise. The comet's surface ices begin to sublimate, turning directly from solid to gas without melting. This process releases dust and small rocky particles embedded in the ice. Jets of gas shoot outward from the nucleus, carrying dust with them. Over time, these emissions form the characteristic tail and coma that make comets visible and spectacular. All that ejected material doesn't disappear. It remains in orbit around the Sun, following a path similar to the comet's orbit, but spreading out gradually. Each time the comet returns to the inner solar system, it sheds more material, adding to the growing stream. Over thousands of orbits, the debris distributes itself along the comet's entire orbital path, forming a tube or ribbon of dust and pebbles that encircles the Sun. When Earth's orbit intersects this ribbon, we experience a meteor shower. The exact timing depends on where the Earth is in its orbit and where the densest parts of the debris stream are located. For most cometary showers, the stream isn't uniform. It has clumps and gaps, denser regions and sparse regions, the result of complex gravitational interactions and the specific history of when and where the comet shed material. Comet Swift-Tuttle, parent of the Perseids, exemplifies this process. Its orbit carries it from beyond Neptune to well inside Earth's orbit. During perihelion passages, when it's closest to the Sun, the comet sheds enormous quantities of material. That material spreads along Swift-Tuttle's orbit, forming the Perseid stream. Because the comet's orbit crosses Earth's orbit at a specific angle and location, we encounter the stream every August when Earth reaches that point in its yearly journey around the Sun. The debris itself is varied in size. Most Perseid particles are tiny, millimeters across or smaller. But the stream also contains larger pebbles, occasionally even small rocks. It's these larger particles that produce the brightest meteors, the fireballs that can briefly outshine Venus or even the Moon. The size distribution follows a power law. Many small particles, fewer medium ones, and very few large ones. This means most meteors you see are produced by dust grain-sized particles, but the memorable fireballs come from pebble-sized or larger chunks. The age of a debris stream varies. Some streams are young, only a few hundred or thousand years old, still closely associated with their parent comet's current orbit. Others are ancient, possibly hundreds of thousands of years old, their particles gradually dispersed by planetary perturbations and solar radiation pressure. As streams age, they spread out, becoming more diffuse and producing lower meteor rates. Fresh streams, where the debris is still concentrated, can produce meteor storms, brief periods of extraordinary activity with thousands of meteors per hour. Asteroid-sourced meteor showers are rarer and more mysterious. Asteroids don't sublimate like comets. They're solid rock or metal, lacking volatile ices. So how do they create debris streams? The answer depends on the specific asteroid and its behavior. For Phaethon and the Geminids, the key is the asteroid's close approach to the Sun. As Phaethon nears perihelion, surface temperatures climb high enough to cause thermal fracturing. Rocks crack. Volatile compounds trapped in mineral grains vaporize. The result is a slow but steady release of dust and small fragments. This isn't as dramatic as cometary outgassing, but over many orbits it accumulates, forming the Geminid stream. Asteroid 2003 EH1, parent of the Quadrantids, might have a different story. It's possible this object was once an active comet that exhausted its ices over time, leaving behind a rocky core. The Quadrantid stream would then be debris shed during its cometary phase, thousands of years ago when it still had volatile material to sublimate. Now dormant and appearing asteroidal, 2003 EH1 continues orbiting, but it's no longer actively contributing to its meteor shower. The Quadrantids we see today are leftover material from a more active past. The distinction between comets and asteroids isn't always clear. Some objects show characteristics of both, like Phaethon with its comet-like orbit but asteroidal appearance. Others transition from one category to the other as they age and lose volatiles. This blurring of boundaries reflects the reality that solar system bodies exist on a spectrum, not in neat categories. Once a debris stream forms, it doesn't remain static. Gravitational forces from planets, particularly Jupiter, gradually perturb the orbits of individual particles. Over time, this can spread the stream out, change its orientation, or even disrupt it entirely. Solar radiation pressure also plays a role, pushing on dust particles and altering their orbits. Smaller particles are affected more strongly, leading to a size-dependent evolution where fine dust drifts away from the mainstream, while larger pebbles remain more closely tied to the parent body's orbit. The result is that meteor streams are dynamic, evolving structures. What we see today is a snapshot of an ongoing process that has played out over millennia and will continue long into the future. Some streams are compact and dense, producing sharp, intense peaks of activity. Others are broad and diffuse, giving us weeks of moderate meteor rates rather than a single night of high activity. Understanding these processes requires both observation and modeling. Astronomers watch meteor showers carefully, recording rates, brightness, and the precise directions meteors come from. This data reveals the stream structure, where it's dense, where it's sparse, how it's distributed in space. Theoretical models then simulate the stream's evolution, tracking how particles move under the influence of gravity and radiation. By matching models to observations, researchers reconstruct the stream's history and predict its future. This work has practical applications. Space debris is a growing concern as we place more satellites in orbit. Some of these satellites pass through meteor streams, encountering enhanced risk during shower peaks. Understanding stream density and structure helps predict these risks. It also informs the design of spacecraft shielding and orbital maneuvers to avoid the most dangerous periods. But beyond practical concerns, studying meteor showers and their parent bodies tells us about the solar system's history. The composition of meteoroid streams reflects the composition of their parent comets and asteroids, which in turn reveals information about conditions in the early solar system when these objects formed. The ice-to-rock ratio in cometary debris, the types of minerals present, the isotopic signatures of various elements. All of this provides clues about where and when the parent body formed. Some meteoroids even reach the ground as meteorites, allowing direct laboratory analysis. Though shower meteoroids rarely survive to become meteorites, they're usually too small and fragile. Related objects sometimes do. Analyzing these meteorites reveals detailed chemistry and mineralogy, information that would be impossible to obtain any other way. The three major showers of 2025 illustrate the diversity of parent bodies. Swift-Tuttle is a large, active comet on a long-period orbit. Phaethon is a small asteroid with an extreme orbit that causes unusual mass loss. 2003, EH1 is something in between, possibly a transition object that was once active but is now dormant. Together, they represent different pathways to creating meteor showers, different mechanisms of mass loss, and different stages in the evolution of small solar system bodies. As you watch meteors in 2025, whether Quadrantids in January, Perseids in August, or Geminids in December, you're witnessing the final moments of ancient travelers. Each meteor is a fragment of its parent body, released years or centuries ago, now completing its journey by burning up in Earth's atmosphere. That parent body continues its orbit, still shedding material, still contributing to the debris stream. And that stream continues to evolve, shaped by gravity and radiation, slowly changing, but persisting across millennia. It's a cycle that began billions of years ago and will continue long after we're gone. a cosmic dance playing out on timescales that dwarf human history. The dance of Earth and debris, orbital mechanics, and viewing windows. Meteor showers are predictable because orbits are predictable. Once you know the path of a debris stream and the path of Earth around the Sun, you can calculate precisely when and where the two will intersect. This is pure orbital mechanics. The mathematics first fully developed by Johannes Kepler in the early 17th century and refined by Isaac Newton later that same century. The same principles that govern planetary motion govern meteor streams, and those principles allow astronomers to predict meteor showers with remarkable accuracy. Earth's orbit is nearly circular, taking 365.25 days to complete one revolution around the Sun. As Earth moves, it sweeps through different regions of space, encountering various debris streams at specific times of year. The Quadrantid stream intersects Earth's orbit in early January, the Perseids stream in August, the Geminids stream in December. These dates remain consistent year after year, shifting only slightly due to minor perturbations and the complexities of orbital dynamics. The intersection isn't instantaneous. Earth is a moving target, and debris streams have width. It typically takes Earth several days to fully traverse a meteor stream, which is why most showers last for a week or two, with activity ramping up, peaking, and then declining as Earth enters, passes through, and exits the stream. The exact duration depends on the stream's width and density distribution, as well as the angle at which Earth crosses it. The Quadrantids' unusually brief peak demonstrates this. Relationship. Earth crosses the Quadrantid stream at a nearly perpendicular angle, slicing through the densest region in just a few hours. Other showers have longer peaks because Earth's path through them is more oblique, spending more time in the dense core. The Perseids, for instance, maintain good activity for several days because their stream is broader, and Earth's trajectory through it is more gradual. Viewing geometry matters enormously. The radiant point, the spot on the sky from which meteors appear to radiate, changes position throughout the night as Earth rotates. When the radiant is below the horizon, you can't see any meteors from that shower because the meteoroids are striking the opposite side of Earth. As the radiant rises, meteor rates increase. When it reaches its highest point, directly overhead, rates maximize because you're looking straight into the stream, encountering meteoroids head-on. This is why most meteor showers are best observed in the pre-dawn hours. As Earth rotates through the night, the observer's location gradually turns to face forward into Earth's orbital motion. By local midnight, you're on Earth's leading edge, the side facing forward along our orbit. By dawn, you're pointing almost directly into the stream. It's like the windshield effect. The front of a moving car encounters more raindrops than the back. The Geminids are an exception. Their radiant rises in the early evening and is already well placed by 10 o'clock p.m. This makes them more convenient for casual observers who don't want to stay up until 3 o'clock a.m. But even for the Geminids, rates increase as the night progresses and the radiant climbs higher. The later you watch, up until the peak hour around 2 o'clock a.m., the more meteors you'll see. The mathematics behind meteor rates involves a parameter called the zenithal hourly rate, ZHR. This represents the number of meteors a single observer would see under ideal conditions. Perfectly dark sky, no light pollution, no moon, with the radiant at the zenith, directly overhead. Real conditions never match this ideal, so actual observed rates are always lower than the published ZHR. Converting ZHR to expected hourly rates requires accounting for several factors. First, the radiant's altitude. If it's not at the zenith, you'll see fewer meteors. There's a mathematical correction factor based on the radiant's angle above the horizon. Second, sky quality. Light pollution, moonlight, or atmospheric haze all reduce visibility. Each magnitude of limiting stellar visibility, the faintest stars you can see, roughly corresponds to a specific reduction factor for meteor rates. Finally, observer experience and attentiveness play a role. Experienced observers spot more faint meteors than beginners. All these corrections can be calculated, allowing you to predict how many meteors you'll likely see from your specific location under actual conditions. Online calculators and mobile apps can do this automatically, taking your location, the date and time, local sky conditions, and the shower's parameters to generate a personalized estimate. These predictions aren't perfect, but they're usually reasonably accurate, giving you a realistic expectation of what you might observe. The speed at which meteoroids enter the atmosphere depends on their orbit relative to Earth. Meteoroids in prograde orbits, moving in the same direction as Earth around the Sun, have lower relative velocities. Meteoroids in retrograde orbits, moving opposite to Earth, have much higher relative velocities because Earth and the meteoroid are essentially colliding head-on. The maximum possible geocentric velocity for solar system meteoroids is about 72 kilometers per second, achieved when a meteoroid on a retrograde orbit at the Sun's escape velocity meets Earth. Different showers have different entry speeds. The Leonids, at 71 km/s, are among the fastest. The Perseids, at 60 km/s, are quite fast. The Geminids, at 35 km/s, are moderate. And some minor showers, like the Draconids, are quite slow at around 20 km/s. These velocity differences affect everything. How bright the meteors are, how long they last, how high in the atmosphere they begin to glow, and what colors they display. Fast meteors start glowing at higher altitudes because their tremendous kinetic energy heats the surrounding air more effectively. A Leonid might begin glowing at 120 kilometers altitude. A slower Draconid might not glow until it reaches 65 kilometers. Similarly, fast meteors burn up higher, rarely penetrating below 80 kilometers. Slow meteors can survive lower, sometimes reaching 40 or 50 kilometers before completely ablating. Entry angle also matters. Meteoroids arriving nearly vertically plunge through the atmosphere quickly, producing short, bright trails. Meteoroids arriving at shallow angles skim through the upper atmosphere, producing long-lasting Earth grazers. The distribution of entry angles varies throughout the night. Early in the night, when the radiant is near the horizon, all meteors arrive at shallow angles. As the radiant climbs, the distribution includes more vertical entries. The beauty of orbital mechanics is its precision. Given accurate orbital elements for a meteor stream and Earth, astronomers can predict not just when the shower will occur, but exactly what rates to expect, when peaks will happen, and even forecast potential outbursts years or decades in advance. When models predict an outburst based on Earth passing through a particularly dense filament of debris, those predictions usually verify. In 1998, models correctly predicted a Leonid storm. In 2011, models predicted a Draconid outburst, and it occurred as predicted. This predictive power comes from centuries of observations and decades of sophisticated computer modeling. Modern simulations track individual meteoroids through space, accounting for gravitational perturbations from every planet, the sun's radiation pressure, and even the effects of relativity for high-velocity particles. These simulations can reconstruct where meteoroids were thousands of years ago and predict where they'll be thousands of years hence. For observers in 2025, this means reliable forecasts. The Quadrantid peak time of 15 o'clock to 18 o'clock UT on January 3rd isn't a guess. It's based on models that have been refined over decades and confirmed by observations. Similarly, the Perseid peak around 07 o'clock to 08 o'clock UT on August 13th and the Geminid peak around 03 o'clock UT on December 14th are solid predictions, likely accurate within an hour or two. There's always some uncertainty, of course. Meteor streams aren't perfectly uniform, and Earth's atmosphere adds variability through its dynamic behavior. But these uncertainties are small compared to the overall predictability. When astronomers say a shower will peak on a certain date at a certain time, they're confident in that prediction to within a few hours. This reliability makes planning possible. You can check predictions weeks in advance. Note the peak dates on your calendar. Arrange time off work or school. Plan travel to a dark site. Coordinate with friends or family. And invest in preparation. Knowing there's a very good chance you'll be rewarded with a spectacular show. Few natural phenomena are this predictable. Meteor showers belong to a rare category of events we can anticipate with confidence, courtesy of orbital mechanics and the patient work of meteor astronomers worldwide. The art and science of observation. From ancient eyes to modern networks. Humans have watched meteor showers for thousands of years, but our understanding and methods of observation have evolved dramatically. Ancient observers simply looked up and marveled. Modern scientists deploy radar arrays, automated cameras, and sophisticated software to capture and analyze every detectable meteor. Yet despite all this technology, the basic experience remains the same. Lying back under a dark sky, watching and waiting for the next streak of light. The earliest recorded meteor observations come from ancient China, Japan, and Korea. Scholars at imperial courts meticulously recorded celestial phenomena, including meteor showers. The Perseids appear in Chinese records dating to 36 CE, described as more than 100 meteors flew through the morning, on a date corresponding to mid-August. Similar records exist for other showers, often described in poetic language that captures both the wonder and the surprise these events inspired. Medieval and Renaissance Europeans saw meteors as omens, signs from heaven that required interpretation. The sudden appearance of numerous falling stars was noted in chronicles and treated as portending major events, good or ill. It wasn't until the scientific revolution of the 17th and 18th centuries that a more empirical approach emerged, with observers attempting to measure the heights, speeds, and trajectories of meteors rather than simply recording their occurrence. The breakthrough came in the 19th century. In November 1833, a spectacular Leonid storm produced thousands of meteors per hour over North America. Observers were stunned. Newspapers ran detailed accounts. Artists created illustrations showing meteors streaming across the sky like snowfall. This event galvanized scientific interest. Observers realized these showers were predictable, recurring phenomena worth systematic study. Denison Olmsted, a Yale professor, collected eyewitness accounts from across the United States and recognized that all the meteors appeared to radiate from the constellation Leo. This was the first clear identification of a radiant point. Within a few decades, astronomers had identified several major showers, calculated their radiance, and connected them to specific parent comets. The field of meteor astronomy was born. Visual observation remained the primary method well into the 20th century. Skilled observers would spend hours under the stars, counting meteors, noting their brightness, recording their paths, and estimating their duration. This required patience, good record keeping, and a willingness to endure cold, fatigue, and occasional clouds. The data collected by these dedicated visual observers form the foundation of our understanding of meteor shower behavior. Radio detection revolutionized the field starting in the 1940s. When a meteor streaks through the upper atmosphere, it ionizes the air, creating a temporary column of free electrons. These ionized trails reflect radio waves. By broadcasting a radio signal and listening for reflections, observers could detect meteors even during daylight or through clouds. This opened up new possibilities, allowing continuous monitoring regardless of weather or time of day. Modern meteor radar networks operate constantly, scanning the skies with sensitive receivers. When a meteor occurs, the ionization trail reflects the broadcast signal, creating a brief echo. Sophisticated software analyzes these echoes, determining the meteor's direction, speed, and altitude. Over days and weeks, thousands or millions of meteors accumulate, allowing researchers to map shower activity with unprecedented precision. Video cameras joined the arsenal in the 1990s and 2000s. Inexpensive CCD cameras sensitive enough to record faint meteors became available. Observers set up automated systems that would run all night, capturing meteors on video. Multiple cameras, separated by distance, could triangulate meteor trajectories, calculating precise orbits for each meteoroid before it entered Earth's atmosphere. Today, global networks of automated video cameras watch the skies continuously. The All-Sky Meteor Surveillance System in the United States, the European Fireball Network, and similar networks in Japan, Australia, and elsewhere collectively record hundreds of thousands of meteors annually. This data feeds into central databases accessible to researchers worldwide. The result is an unprecedented understanding of meteor shower structure, composition, and behavior. Citizen scientists contribute significantly. Organizations like the American Meteor Society and International Meteor Organization coordinate observations by amateur astronomers. Observers submit meteor counts, noting the shower, time, location, and sky conditions. This crowdsourced data complements professional observations, providing broader geographic coverage and helping to confirm predictions. Photographing meteors has evolved from an arcane specialty to an accessible hobby. With modern digital cameras, anyone can capture meteors. The technique is straightforward. Set your camera on a tripod, point it at the sky, use a fast lens, f2.8 or wider if possible. Set the ISO high, 1600 to 3200, and take long exposures, 15 to 30 seconds. Over the course of several hours, you'll likely capture multiple meteors. Composite these images together, and you can create stunning visualizations showing dozens of meteors radiating from the shower's radiant point. The details matter though. Lens choice affects what you capture. Wide-angle lenses, 14mm to 24mm on full-frame cameras, capture more sky, increasing your chances of recording a meteor in each frame. But meteors will appear smaller and less detailed. Normal to moderate telephoto lenses, 35mm to 85mm, show meteors with more detail but cover less sky, reducing the probability of capturing one. The ideal compromise for most observers is 24mm to 35mm, wide enough to catch plenty of meteors, but not so wide that they appear tiny. Focus is critical. Achieving sharp focus on stars in darkness isn't trivial. Manual focus, set to infinity, often doesn't work perfectly due to lens manufacturing tolerances. The best technique? Find a bright star, switch to live view, zoom in digitally on that star, and carefully adjust manual focus until the star appears as a tight pinpoint. Then lock focus, tape it in place if necessary, and don't touch it for the rest of the night. Small focus errors that might not matter for daytime photography become obvious when photographing point sources like stars. Exposure settings require balancing multiple factors. Longer exposures collect more light, making faint meteors visible. But they also increase sky glow from light pollution, and if the exposure is too long, stars will trail due to Earth's rotation. A good starting point, 20 seconds at f2.8, ISO 3200. If the sky background is too bright, reduce ISO or shorten exposure. If it's very dark, increase ISO up to 6400 or even 2800 on modern low-noise cameras. Interval shooting is essential. You want continuous coverage, frames taken back-to-back all night with minimal gaps. Most cameras support interval timer shooting, taking a series of exposures automatically. Set it for the maximum exposure time that doesn't produce trailing, usually 20-30 seconds, with minimal interval between frames, and let it run for hours. You'll accumulate hundreds of images, most showing just stars, but a few capturing meteors. Post-processing turns raw images into finished products. First, Eliminate frames with no meteors, satellites, or airplanes. You'll want some airplane trails for comparison with meteors. Then combine the meteor frames. Simple stacking works. Overlay all meteor images on a single star background, aligning stars precisely. More sophisticated approaches use image editing software to selectively blend only the meteor trails, creating a composite that shows numerous meteors on one star field. Some photographers go further, creating animated sequences that show meteors appearing one after another throughout the night. This requires careful alignment of all frames to account for Earth's rotation, then assembling them into a time-lapse video. The result is mesmerizing. Stars wheeling across the sky while meteors streak through the scene, a dynamic visualization of celestial motion. Color in meteor photography depends on camera sensitivity and processing. Most cameras can record color in bright meteors, capturing the greens, yellows, and oranges that visual observers report. Fainter meteors often appear white or gray because they don't emit enough light to trigger the camera's color sensitivity. Post-processing can enhance colors, but care is needed to avoid artificial-looking results. Persistent trains present special challenges and opportunities. These glowing trails that linger after the meteor has vanished show up beautifully in photographs. Because they last several seconds, they're often captured in multiple consecutive frames, showing how atmospheric winds twist and distort the train. Creating an animation of a persistent train requires aligning frames carefully and showing the progression over time. The results reveal atmospheric dynamics at 90 kilometers altitude, wind patterns that can't be seen any other way. Some meteor photographers incorporate foreground objects, placing the meteor shower in context with landscapes. This requires scouting locations in advance, planning compositions during daylight, and carefully positioning the camera to include both interesting foreground and the shower's radiant in the same frame. The results are dramatic. Meteors streaking over mountains, monuments, trees, or bodies of water, connecting the celestial display to specific places on Earth. Advanced techniques include stacking for noise reduction, combining multiple images of the same star field to average out sensor noise, and using tracking mounts that follow stars, allowing longer exposures without trailing. But these aren't necessary for good meteor photography. A basic DSLR or mirrorless camera, a fast wide-angle lens, a sturdy tripod, and patience will yield excellent results. The gratification is immediate. Unlike deep sky astrophotography, which requires extensive processing to reveal faint nebulae or galaxies, meteor photographs show their subject clearly in the raw images. You can review your captures right on the camera's screen, seeing meteors you photographed but might have missed visually because you were looking in the wrong direction. There's a thrill in discovering meteors in your images, especially the faint ones that wouldn't have been visible to the eye. Sharing meteor photographs has never been easier. Social media platforms light up during major shower peaks as observers worldwide post their captures. Photography communities provide feedback and tips. Some images go viral, bringing the beauty of meteor showers to audiences who might never venture out to watch in person. This democratization of astrophotography has created a global community of meteor photographers, from serious enthusiasts with professional equipment to casual observers using entry-level cameras. For those without cameras, smartphones can even capture bright meteors. Modern smartphone cameras with night modes can photograph bright stars, and the brightest meteors will record if you're lucky with timing. Dedicated astrophotography apps provide manual controls, allowing longer exposures and higher ISO settings than the default camera app. While smartphone images won't match DSLR quality, they prove that meteor photography is accessible to nearly everyone. Smartphone apps have made meteor watching more accessible. Apps can identify constellations, show the location of meteor shower radiance, notify you of upcoming peaks, and even estimate expected rates for your location. Some apps include augmented reality features, overlaying constellation patterns, and radiant points on your phone's camera view. While watching meteors on a screen isn't the same as seeing them with your own eyes, these tools help newcomers understand what they're looking at and where to direct their attention. Light pollution remains the greatest challenge for meteor observers. The spread of artificial lighting has dimmed the night sky over vast areas. Suburbs glow with streetlights, parking lot lights, and security lights. Cities are worse. Their upward lights scatter visible from orbit. This light washes out faint stars and makes all but the brightest meteors invisible. Dark sky preservation efforts aim to combat this problem. Organizations like the International Dark Sky Association promote lighting ordinances that reduce unnecessary artificial light. Dark sky parks and reserves protect areas with minimal light pollution. These efforts not only help astronomers and meteor watchers, but also benefit wildlife, reduce energy waste, and reconnect people with the natural night sky. For urban and suburban observers unable to travel to dark sites, there are still strategies. Position yourself to block nearby lights, behind a building, under trees, or simply lying down, so a structure blocks streetlights from your direct view. Let your eyes adapt for at least 20 minutes without looking at any bright lights, including phones. Face away from the worst light pollution, looking toward the darkest part of your sky. These tactics won't match a truly dark sight, but they help. The scientific value of meteor observations extends beyond simply counting how many meteors occur. Each meteor provides data. Trajectory analysis reveals the meteoroid's orbit before it hit Earth. Brightness and light curve analysis, how brightness changes over time, indicates size and mass. Spectroscopy reveals composition, identifying the elements present in the meteoroid. Persistent train observations study upper atmospheric dynamics. Radar data has revealed fascinating structures within meteor streams. Some showers have multiple components, filaments of debris with slightly different orbits that produce separate activity peaks. Others show gaps, regions where planetary perturbations have cleared out material. The three-dimensional structure of debris streams is far more complex than early visual observers imagined. Meteorites from shower meteoroids are extremely rare. Most shower particles are too small and fragile to survive atmospheric entry. They completely ablate at high altitude, never reaching the ground. Meteorites generally come from larger, sturdier objects, sporadic asteroids, not shower meteoroids. However, there have been a few cases where fresh meteorite falls coincided with minor meteor showers, suggesting a possible connection. The study of meteors connects to broader questions in planetary science. Meteor composition reveals the chemistry of comets and asteroids, which form from the same primordial material as planets. The dust that produces meteors once drifted in the solar nebula, the disk of gas and dust surrounding the young sun 4.6 billion years ago. By studying this dust, now preserved in comets and asteroids and eventually burning up as meteors, we glimpse the raw materials from which Earth itself formed. For casual observers, though, the science is secondary to the experience. Watching a meteor shower is fundamentally about wonder, about lying under the stars and seeing the universe in motion. It's accessible, requiring no special equipment or training. It's humbling, reminding us of the vast scales of space and time. And it's beautiful. Each meteor, a brief artwork painted across the canvas of the night. As 2025's showers approach, consider the cumulative weight of all those who've watched before you. Ancient Chinese astronomers recording observations in imperial courts. Medieval monks noting celestial portents. Renaissance scholars attempting measurements. 19th century visual observers painstakingly counting meteors through long winter nights. Modern researchers analyzing radar returns and spectroscopic data. Amateurs photographing meteors from dark backyards. You join this long tradition, adding your observations to millennia of human engagement with these cosmic visitors. Beyond the big three, other meteor showers of 2025. While the Quadrantids, Perseids, and Geminids dominate the annual meteor shower calendar, they're far from the only shows worth watching. 2025 brings numerous other opportunities, some modest but reliable, others variable and unpredictable. Each has its own character, its own parent body, its own story. Here's a brief tour through some of the year's other notable showers. The Lyrids arrive in late April, peaking around April 22nd to 23. This is a moderate shower, typically producing 10 to 20 meteors per hour at peak. What makes the Lyrids notable is their fast meteors, 48 kilometers, and occasional surprises. In some years, brief outbursts boost rates to 50 or more meteors per hour. The parent body is Comet C-1961 G1 Thatcher, a long-period comet that won't return for more than 400 years. The Lyrids are one of the oldest meteor showers on record, with Chinese observations dating back to 687 BCE. In 2025, the Lyrids peak under a waxing crescent moon, which sets early in the evening, leaving the pre-dawn hours dark for optimal viewing. The radiant in Lyra rises around midnight, so the best viewing is from 2 o'clock a.m. until dawn. From mid-northern latitudes, expect 10 to 15 meteors per hour under good conditions, with some meteors leaving persistent trains. The Eta Aquarids peak in early May, around May 6th or 7th. These are actually fragments of Halley's Comet, the same body that produces the Orionids in October. The Eta Aquarids are a southern hemisphere shower, best seen from tropical and southern latitudes where the radiant rises higher. Northern observers see reduced rates due to the low radiant. The meteors are fast, 66 kilometers, and often leave persistent trains. In 2025, the peak falls just after a first quarter moon, which sets around midnight, leaving the pre-dawn hours reasonably dark. Southern observers with clear skies might see 30 to 40 meteors per hour. Northern mid-latitude observers will see significantly fewer, perhaps 10 to 15. Still worth watching if you're up before dawn, especially to catch the fast Eta Aquarid meteors and their beautiful trains. The Orionids return in late October, peaking around October 21st, 22. Like the Eta Aquarids, these are Halley's Comet debris. The Orionids are more favorable for northern hemisphere observers, with the radiant rising in the evening and reaching a good altitude by midnight. Typical rates are 15 to 20 meteors per hour, though like the Lyrids, the Orionids occasionally surprise with higher rates. They're fast meteors, 67 kilometers that often fragment, producing brief flashes and fireballs. October 2025 brings a new moon on the 21st, providing ideal dark sky conditions for the Orionids. This is one of the year's best opportunities for a moderate shower under perfect conditions. Expect 15 to 25 meteors per hour after midnight, with some bright meteors and persistent trains. The only challenge is October weather, which can be variable in many regions. The Leonids peak around November 17th to 18th. This shower is famous for producing spectacular meteor storms approximately every 33 years when Earth passes through fresh debris trails from the parent comet, 55P Tempel-Tuttle. The last major storms occurred in the late 1990s and early 2000s. We're now in a quiet phase, with typical rates around 10 to 15 meteors per hour. But Leonid meteors are the fastest of all major showers, 71 kilometers, producing brilliant, colorful meteors with long, persistent trains. In 2025, the moon is in a waning crescent phase, rising around 3 o'clock a.m. The hours between midnight and moonrise offer the best viewing. Expect modest rates but spectacular individual meteors. Leonids are also famous for fireballs and earth grazers, so even with low rates, the quality can be exceptional. Several torrid streams are active in October and November. The South Torrids peak around November 5th, and the North Torrids peak around November 12th. These showers are slow, so 27 kilocumulars, but are associated with an unusually high proportion of fireballs. The torrids don't produce high rates, typically 5 to 10 per hour, but they're known for bright, colorful meteors. The parent body is Comet 2P Encke, a short period comet on an unusual orbit. Unfortunately, both torrid peaks in 2025 occur around the time of a full moon, November 5th, severely limiting visibility. Only the brightest fireballs will be visible through the moonlight. If you're meteor watching in early November, expect to see a few bright torrids among other shower and sporadic meteors, but rates will be suppressed. The Perseids close out the year, peaking around December 22-23. This is a minor shower, typically producing only 10 meteors per hour at best, sometimes fewer, but it peaks around the winter solstice. And in 2025, the moon is a thin, waning crescent, not interfering at all. The radiant is circumpolar for northern hemisphere observers, meaning it never sets. This allows viewing throughout the night. The parent body is Comet 8P Tuttle, and the shower occasionally produces brief outbursts with higher rates. For observers who've just watched the Geminids a week earlier, the Perseids offer a quiet coda to the year's meteor watching, a modest but reliable shower visible during the longest nights of the year. Don't expect high rates, but in the stillness around the winter solstice, even a few meteors can be magical. Numerous minor showers fill out the calendar. The Delta Aquarids in July, the Alpha Capricornids in late July, the Draconids in October, and many others. Most produce low rates, often just a few meteors per hour, barely above the sporadic background. But meteor enthusiasts track them all, collecting data that helps refine our understanding of these small debris streams. Sporadic meteors occur constantly, unassociated with any recognized shower. On any given night, under dark skies, you might see 5 to 10 sporadic meteors per hour. During a shower, these sporadics continue, adding to the shower meteors. Distinguishing sporadics from shower meteors is straightforward. Shower meteors appear to radiate from the radiant point, while sporadics come from random directions. The overall meteor calendar for 2025 offers something almost every month. No matter when you look up, there's a chance of seeing meteors. The three major showers, Quadrantids, Perseids, Geminids, provide the best opportunities, with high rates and good visibility. But the minor showers, taken together, offer a steady rhythm of celestial activity throughout the year. Each shower adds variety, different speeds, different colors, different characteristics that make meteor watching endlessly fascinating. For observers who catch the meteor watching bug, the calendar becomes a guide to the year. January means Quadrantids. Late April, the Lyrids. August, of course, belongs to the Perseids. October brings Orionids and Draconids. November offers Leonids and Taurids. And December closes with the Geminids and Perseids. Following this rhythm connects you to cosmic cycles, to the predictable intersections of Earth's orbit with ancient debris streams. It's a calendar written not in human time, but in the patient revolutions of comets and the slow dispersal of dust across millions of kilometers. The atmosphere's role, where stars burn. When a meteoroid enters Earth's atmosphere at tens of kilometers per second, it encounters resistance for the first time in its existence. For millions of years, perhaps, it has drifted through the vacuum of space, encountering nothing, feeling no drag. But Earth's atmosphere, though thin by our standards, is dense enough to stop a cosmic traveler. The meteoroid's journey ends here, transformed from a cold, dark pebble into a brilliant streak of light that exists for less than a second. The process begins at surprisingly high altitude. Most meteors start to glow between 80 and 120 kilometers above the surface, depending on their speed and size. At this height, the atmosphere is incredibly thin, less than 1/1,000,000th the density at sea level. Yet even this trace atmosphere is enough to affect an object moving at 35 to 70 kilometers per second. As the meteoroid plows through the tenuous upper atmosphere, it compresses the air in front of it. This compression heats the air to thousands of degrees Celsius in a fraction of a second. The superheated air molecules collide violently with the meteoroid's surface, transferring energy. Surface material vaporizes, atom by atom, creating a cloud of glowing gas around the meteoroid. This glowing envelope is what we see as a meteor. Ionization plays a crucial role. The extreme temperatures strip electrons from atoms, creating a plasma trail behind the meteor. This ionized column persists for a few seconds after the meteor passes, gradually recombining as electrons rejoin atoms. Some meteors leave trails visible for several seconds, glowing faintly as the recombination process continues. These are the persistent trains, beautiful glowing streaks that twist and distort in the upper atmospheric winds. The height at which meteors burn depends primarily on their entry speed. Fast meteors like Leonids start glowing higher, around 110 to 120 kilometers. Their tremendous kinetic energy heats the atmosphere more effectively at higher altitudes where the air is thinner. Slower meteors like Draconids don't begin glowing until they reach denser air at 65 to 70 kilometers altitude. Similarly, the altitude at which meteors completely ablate varies. Fast meteors typically burn up completely between 80 and 100 kilometers. Slower meteors can survive lower, sometimes reaching 50 or 60 kilometers before fully disintegrating. Only the largest, sturdiest meteoroids survive to lower altitudes, and only a tiny fraction of those reach the ground as meteorites. The color of a meteor reveals its composition. Different elements emit characteristic wavelengths when heated to plasma temperatures. Sodium glows yellow-orange. Magnesium produces brilliant green. Calcium emits violet. Iron contributes white and yellow hues. Observing these colors requires good dark adaptation and a bit of luck, as most meteors are too brief and too faint for our eyes to register color. But bright meteors often show distinct hues, flashing green or orange or blue as they streak across the sky. Spectroscopy allows precise measurement of these colors. By passing a meteor's light through a prism or diffraction grating, researchers can spread it into a spectrum showing exactly which wavelengths are present. This reveals not just general composition, but specific elements and their relative abundances. A spectroscopic analysis of a single bright meteor can determine that it contains, for example, sodium, magnesium, iron, calcium, and trace amounts of chromium and nickel, all in specific ratios that indicate the meteoroid's parent body and formation history. Sound from meteors is rare, but occasionally reported. Observers sometimes hear hisses, pops, or crackles during bright meteors. This phenomenon, called electrophonic sound, isn't caused by the meteor's passage directly. At 80 kilometers altitude, no sound could reach the ground in real time. Instead, it's thought to result from VLF, very low-frequency radio waves, generated by the meteor's ionization trail, interacting with conductive objects near the observer, such as eyeglasses, hair, or leaves. These objects act as transducers, converting the radio waves into audible sound. The effect is subtle and controversial, but multiple observers have reported it consistently. Meteor fragmentation occurs when a meteoroid isn't structurally strong enough to withstand atmospheric stresses. As the pressure builds up, weak points crack, and the meteoroid breaks into pieces. Each fragment continues on a slightly different trajectory, producing a cluster of parallel streaks, or a single meteor that appears to flare and split. Highly fragile meteoroids, perhaps composed of loosely bound dust, can undergo catastrophic fragmentation, producing brief but spectacular fireballs that suddenly brighten and fragment into multiple pieces before vanishing. Meteorite-producing events are different. When a meteoroid is large and strong enough, typically at least a few centimeters across, and composed of solid rock or metal, it can survive the trip through the atmosphere. These events produce very bright meteors, often fireballs that cast shadows and persist for several seconds. The meteoroid slows dramatically as it descends, eventually reaching a velocity where ablation stops, around 5 to 10 kilometers per second. The surviving fragment or fragments then fall the rest of the way in dark flight, no longer glowing, dropping like any falling object. But these are rare and almost never associated with meteor showers. Shower meteoroids are too small and fragile. Nearly all meteorites come from sporadic meteoroids, asteroids that weren't part of any organized stream. So, while you might see thousands of meteors during a shower, you'd never find meteorites from them afterward. The upper atmosphere is affected by meteor influx. Earth accumulates an estimated 15,000 to 40,000 tons of extraterrestrial material annually, most of it dust from meteor ablation. This dust settles slowly through the atmosphere, taking years to reach the ground. Along the way, it interacts with atmospheric chemistry, provides nucleation sites for clouds, and contributes trace elements to the environment. The ionization produced by meteors also affects the ionosphere, the layer of charged particles that reflects radio waves. During major meteor showers, enhanced ionization allows radio amateurs to make long-distance contacts by bouncing signals off meteor trails. This is called meteor scatter communication, and it provides a practical application of meteor science. The mesosphere, where most meteors burn, is one of the least understood regions of Earth's atmosphere. Too high for balloons, too low for satellites, it's difficult to study directly. Meteors provide one of the few ways to probe this region, acting as natural probes that reveal temperature, density, and wind patterns at 80 to 100 kilometers altitude. Noctilucent clouds, those rare, beautiful ice clouds that form at the mesopause around 85 kilometers, may be related to meteor dust. These clouds require extremely cold temperatures and nucleation sites for ice crystals to form. Meteor dust could provide those sites, linking two spectacular atmospheric phenomena: shooting stars and ghostly high-altitude clouds that glow in the twilight sky. As you watch meteors in 2025, you're witnessing the atmosphere at work. Each streak of light represents not just a meteoroid, but the interaction between that object and the gases that surround Earth. The glow is atmospheric molecules releasing energy, excited by collisions with vaporized meteoroid atoms. The trail is ionized air, slowly recombining in the thin winds of the mesosphere. The colors are elemental signatures. Characteristic emissions of atoms that formed 4.6 billion years ago in the disk of dust and gas that surrounded the young sun. The atmosphere, often invisible and taken for granted, reveals itself in these moments, briefly outlined in light by visitors from space. It's protective, stopping these high-speed projectiles before they can reach the surface. It's dynamic, with winds and temperatures that twist and distort meteor trails. And it's beautiful, transforming cosmic debris into one of nature's most spectacular displays. What we learn: the scientific value of meteor showers. Meteor showers aren't just pretty lights in the sky. They're scientific gold mines, offering data that spans multiple fields of research, from planetary science to atmospheric physics, from orbital dynamics to astrobiology. Every meteor that streaks overhead carries information, and collectively, the hundreds of thousands of meteors observed each year build a picture of our solar system's past and present. The most direct information comes from composition. When spectroscopes analyze meteor light, they reveal which elements are present and in what ratios. This tells us what the parent body, the comet or asteroid that shed this material, is made of. Comparing compositions across different showers reveals patterns. Cometary meteors tend to be rich in volatiles and organics. Asteroidal meteors are typically more silicate-rich with less carbon. These compositional signatures connect to the conditions in the early solar system. Different regions of the protoplanetary disk had different temperatures and chemical environments. Objects forming near the Sun developed different compositions than those forming in the cold outer regions. By analyzing meteoroid composition, researchers can infer where and when the parent body formed, reconstructing aspects of solar system history that no other technique can access. Orbital data provides another layer of insight. By triangulating meteor trajectories, researchers calculate the precise orbit each meteoroid followed before encountering Earth. Thousands of these individual orbits, combined, map out the three-dimensional structure of the debris stream. Are the meteoroids clustered tightly around the parent body's orbit, or spread widely? Are there gaps or dense filaments? How has planetary gravity reshaped the stream over time? This helps answer fundamental questions about how debris streams form and evolve. When do particles ejected from a comet disperse into a broad stream? How long does it take? What role do planetary perturbations play? Can we predict when Earth will encounter dense regions and produce outburst activity? Modern computer simulations, validated against observed stream structures, have reached remarkable sophistication, modeling individual meteoroids over thousands of orbital revolutions. Meteor studies also contribute to our understanding of comets themselves. How often do comets shed material? What mechanisms drive mass loss? How much material do they lose each orbit? These questions can't be answered by observing comets directly. They're only active when near the Sun, and measurements are difficult. But the debris streams they leave behind preserve a record of past activity. By modeling the stream's age and mass distribution, researchers infer the comet's mass loss history over millennia. The recent recognition that some meteor showers come from asteroids has opened new questions. How do asteroids lose material? What processes operate on bodies that lack volatile ices? The study of Phaethon and the Geminids has revealed thermal fracturing as a potential mechanism, offering insights into how rocky bodies evolve in extreme environments. This has implications beyond meteor showers, affecting our understanding of near-Earth asteroids and impact hazards. Meteor science intersects with astrobiology through the study of organic compounds. Some meteoroids, particularly those from primitive comets, contain complex organic molecules, amino acids, polycyclic aromatic hydrocarbons, even sugar molecules. These compounds form in space through various processes and are preserved in cometary ice for billions of years. When delivered to the early Earth via meteoroids, they could have contributed to the chemical inventory that eventually gave rise to life. We can't easily recover these organics from meteors. They're vaporized in the atmosphere. But we can detect them spectroscopically, and we can study related material in meteorites that survived atmospheric entry. The connection between meteor showers and the delivery of organics to Earth remains an active area of research, linking astronomy, chemistry, and biology. Atmospheric science benefits from meteor observations too. The ionization trails left by meteors affect radio wave propagation, atmospheric chemistry, and possibly cloud formation. Meteors also provide one of the few direct probes of the mesosphere, that difficult-to-study region between 50 and 100 kilometers altitude. By tracking how meteors ablate, researchers infer atmospheric density and temperature at these heights. The cumulative influx of extraterrestrial material, tens of thousands of tons per year, has geochemical implications. Over Earth's history, this steady rain of cosmic dust has contributed trace elements to the crust and oceans. Some researchers suggest that periods of enhanced meteor influx, perhaps caused by the breakup of large comets, might have triggered climate effects through increased atmospheric dust or altered chemistry. While controversial, these ideas highlight how interconnected different aspects of Earth science are. Hazard assessment is another practical application. While meteor showers consist of tiny harmless particles, studying them helps us understand the larger population of objects in near-Earth space. The same comets and asteroids that produce meteor showers also occasionally produce larger fragments that could pose impact hazards. Understanding how these objects break apart, how their debris disperses, and how planetary gravity affects their orbits informs efforts to detect and potentially mitigate asteroid impact risks. The predictability of meteor showers has made them useful for spacecraft operations. Satellites and space stations can adjust their orbits or orient shielding to minimize risk during major showers. The International Space Station has occasionally performed debris avoidance maneuvers to reduce collision risk. While the probability of a serious impact is low, the consequences could be severe, so preventive measures are worthwhile. Culturally and historically, meteor showers remind us of our connection to the cosmos. The same showers our ancestors watched thousands of years ago still occur, linking us across time to those ancient observers. The predictability that allows modern astronomers to forecast showers also demonstrates the order underlying natural phenomena, a key principle that drove the scientific revolution. Meteor showers are accessible science, requiring no specialized equipment, no advanced degree, just willingness to look up and pay attention. For students and educators, meteor showers offer hands-on learning opportunities. Counting meteors teaches observation skills and data collection. Photographing meteors introduces astronomical imaging. Analyzing meteor spectra introduces spectroscopy. Modeling debris streams introduces orbital mechanics. A single meteor shower can motivate exploration across multiple scientific disciplines, making it an ideal educational tool. As research continues, new techniques reveal new insights. Machine learning algorithms now analyze thousands of video-recorded meteors automatically, extracting trajectories and light curves far faster than human observers could. Space-based observations from satellites detect meteors from above, offering unique perspectives. And the upcoming missions to asteroids and comets, including Japan's planned flyby of Phaethon, will provide ground truth for models derived from meteor observations. The value of meteor showers extends beyond any single discovery or data point. They represent ongoing, accessible natural phenomena that connect multiple scientific disciplines. They offer annual opportunities for public engagement with astronomy. They provide historical continuity, linking modern science to observations spanning millennia. And they serve as reminders that Earth is not isolated, but embedded in a dynamic solar system filled with objects large and small, some posing potential hazards, others enriching our understanding of how planets form and evolve. Every meteor you see in 2025, whether a bright Geminid fireball or a faint Perseid streaking past, contributes to this larger enterprise. Not every meteor is recorded or analyzed, but the collective phenomenon of millions of meteors annually provides the data that drives progress. In a sense, watching meteors is participating in science, joining a community of observers that spans centuries and continents, all united by curiosity about those brief flashes of light that connect Earth to the cosmos beyond. Light pollution, the invisible thief of night. Before we close our journey through 2025's meteor showers, we must address the single greatest challenge facing meteor observers today: light pollution. This modern scourge has transformed the night sky across vast areas of the planet, dimming stars and rendering all but the brightest meteors invisible. Understanding light pollution and efforts to combat it is essential for anyone serious about meteor watching in the 21st century. A century ago, the Milky Way was visible from nearly every location on Earth. Cities glowed softly with gas lights and early electric illumination, but the night sky remained largely pristine. Someone standing in New York City or London could look up and see thousands of stars, the dusty band of our galaxy, stretching from horizon to horizon. Meteor showers were spectacular even from urban locations. Today, the situation is drastically different. According to research published in Science Advances, more than 80% of the world's population lives under light-polluted skies. In the United States and Europe, that figure rises above 99%. The Milky Way has become invisible to 1/3 of humanity, including 60% of Europeans and 80% of North Americans. For many children growing up in cities today, the idea that the sky could be filled with thousands of stars is as foreign as the concept of a pre-industrial world. Light pollution comes from multiple sources, but the primary culprit is poorly designed outdoor lighting. Street lights, parking lot lights, security lights, and architectural lighting often shine upward as well as downward, wasting energy and scattering light into the night sky. This scattered light reflects off water droplets, dust particles, and air molecules in the atmosphere, creating an artificial glow called sky glow that can be visible from dozens or even hundreds of kilometers away. The effects on meteor observation are profound. Under truly dark skies, with a limiting magnitude of 6.5 or better, observers can see meteors as faint as magnitude +5 or +6, detecting numerous shower members that would be invisible in brighter conditions. Under suburban skies, with a limiting magnitude of 4.0, only meteors brighter than magnitude +2 or +3 are visible. That difference represents a factor of 10 to 20 in the number of visible meteors. A shower that produces 50 meteors per hour in dark skies might yield only 5 to 10 from a suburban location. Light pollution affects more than astronomy. Ecological studies have documented its impacts on wildlife, from sea turtle hatchlings becoming disoriented by beachfront lights to migratory birds thrown off course by illuminated buildings. Human health is affected too, with artificial light at night linked to sleep disruption, circadian rhythm disorders, and even increased cancer risk in shift workers. The economic cost is staggering, with billions of dollars in electricity wasted annually on upward-directed light that serves no useful purpose. Fighting back requires both technology and policy. The International Dark Sky Association, founded in 1988, leads efforts to reduce light pollution through education, advocacy, and certification programs. They promote dark sky-friendly lighting designs that direct light downward where it's needed, rather than upward where it creates sky glow. Fully shielded fixtures, warm spectrum LEDs, which produce less blue light that scatters more easily, and motion sensors that illuminate only when needed all help reduce the problem. Dark sky places, certified by the IDA, offer refuges for stargazers and meteor watchers. These include dark sky parks, protected areas with exceptional starry skies, and dark sky reserves. Larger regions that include both core dark zones and peripheral areas working to improve lighting. As of 2025, more than 200 locations worldwide have earned Dark Sky Place certification, from small parks to entire islands and municipalities. Visiting a dark sky place transforms the meteor watching experience. Under skies so dark you can read by the light of the Milky Way, meteor showers come alive. Faint meteors that would be invisible in cities streak across the heavens. The radiant point stands out clearly, surrounded by thousands of stars. Colors become visible in brighter meteors, and persistent trains, those glowing trails that linger after the meteor passes, appear frequently and remain visible for longer. The contrast is stark. Consider the Geminids under different conditions. In a major city with severe light pollution, you might see 5 to 10 meteors per hour at peak. In a moderately dark suburban location, 15 to 25. In a rural area with minimal light pollution, 40 to 60. And in a certified dark sky place with truly pristine skies, 100 or more. The shower doesn't change. What changes is how much of it you can see. Some observers take extreme measures to escape light pollution. Desert regions in the American Southwest, particularly parts of Arizona, New Mexico, and West Texas, offer some of the darkest skies in North America. The Atacama Desert in Chile boasts the darkest skies on Earth, attracting professional observatories and amateur astronomers alike. Australia's outback, parts of Namibia, and remote locations in northern Canada all provide exceptional viewing. But traveling to these distant dark sites isn't necessary for everyone. Even modest efforts to reduce local light pollution help. Observers have successfully improved their viewing conditions by working with neighbors to shield outdoor lights, persuading local businesses to turn off parking lot lights after closing, or convincing municipalities to upgrade streetlights to fully shielded, motion-activated models. Small changes accumulate, and even a modest improvement in sky brightness can significantly enhance meteor visibility. Technology offers solutions too. Bortle scale, sky quality meters, available as smartphone apps. Measure sky. Brightness objectively, helping observers find the darkest accessible locations near them. Light pollution maps, updated regularly with satellite data, show the extent of light pollution across entire continents, making it easy to identify dark sky sites within a reasonable drive. Planning apps incorporate these maps, suggesting optimal viewing locations for any given meteor shower based on predicted rates, moon phase, and local sky brightness. The fight against light pollution is gradually gaining traction. Cities like Flagstaff, Arizona, have maintained strict lighting ordinances for decades to protect nearby observatories. France passed national legislation in 2013 requiring commercial buildings to turn off lights after 1 a.m. Slovenia declared dark sky protection a national priority. These examples demonstrate that policy solutions are possible and that public support for preserving the night sky exists. For meteor watchers in 2025, the message is clear. Seek out darkness. Check light pollution maps. Plan trips to dark sky sites during major shower peaks. Support local efforts to reduce unnecessary lighting. And when you do find a dark location, cherish it. These places are becoming rarer, but they're where meteor showers reveal their full glory, where the connection between Earth and cosmos feels immediate and profound. Standing under truly dark skies, watching meteors streak by overhead, you understand what's been lost in our over-illuminated world, but you also understand what can be preserved, what can still be shared with future generations if we act now to protect these last refuges of natural darkness. The meteor showers don't care about our lights. They'll continue whether we see them or not. But we should care, because in losing the night sky, we lose something essential, a connection to the universe that has inspired humanity since our ancestors first looked up and wondered at the lights moving across the darkness. Closing. The hidden pattern. The sky turns. The earth spins. And somewhere above, particles older than memory drift through the vacuum, patient travelers on billion-year journeys. Some will burn tonight, transforming themselves into light and heat in the faint ionized trails that slowly fade in the cold mesosphere. Others will continue drifting, waiting for future centuries, future encounters, future eyes to witness their final moments. You have journeyed through 3 of the year's most magnificent meteor showers, and if you've been paying attention, you might have noticed something remarkable. Something the ancient astronomers who first recorded these showers couldn't have known. Something that only becomes clear when you step back and see the bigger picture. All 3 of these showers, these supposedly eternal celestial rhythms, are relatively new to human awareness. The Geminids weren't recorded until 1862. The Quadrantids were first noted in the 1830s, though they were initially confused with other minor showers. Even the Perseids, though observed since 36 CE, weren't recognized as a distinct, predictable shower until the 19th century, when Italian astronomer Giovanni Schiaparelli connected them to Comet Swift-Tuttle in 1866. What changed? Why did humanity suddenly discover meteor showers in the 1800s after watching the skies for millennia? The answer isn't that the showers suddenly appeared. It's that we finally had the scientific framework to understand what we were seeing. Before the 19th century, meteors were atmospheric mysteries, shooting stars that might appear on any night for unknown reasons. The idea that they came from space, that they followed predictable patterns, that they were connected to comets and orbits around the sun, this was revolutionary. But here's the twist that should make you rethink everything you've just learned. Some of these showers genuinely are new. The Geminids are intensifying. They're stronger now than they were 150 years ago. And based on the evidence, they may not have been visible at all before the 1800s. The debris stream is young, still forming, actively growing. This means we're living in a special moment. A brief window, cosmically speaking, when these particular meteor showers exist in their current form. 1,000 years ago, the night sky looked different, not because humans lacked telescopes, but because the actual celestial phenomena were different. And 1,000 years from now, they'll be different again. Some showers will have faded, their streams dispersed. Others will have emerged. New debris fields created by fresh cometary outbursts or asteroid disruptions. The Quadrantids with their narrow 6-hour peak. The Perseids traced back to a comet that was once labeled the most dangerous object in the solar system. The Geminids from an asteroid that shouldn't be able to produce meteors at all. These aren't just random shows in the sky. They're evidence of ongoing processes, dynamic evolution. The solar system's still settling, still changing, still becoming. When you watch a meteor in 2025, you're not seeing something eternal and unchanging. You're witnessing a moment in time, a snapshot of a system in flux. That particle burning up overhead might be from a comet that passed through thousands of years ago, or it might be from material shed just decades ago. The meteor shower it belongs to might persist for millions of years, or it might fade within a few centuries. This perspective transforms meteor watching from passive observation into something more active, almost urgent. These showers won't always be here, not in this form. Not with these characteristics. The Geminids you see in 2025 are likely brighter, more numerous than they'll ever be again in human history. The Quadrantids might fade away completely if their parent body stops shedding material. Even the reliable Perseids will eventually disperse, their stream too diffuse to produce significant meteor rates. So when you look up this year, whether in January, August, or December, remember, you're not just watching a meteor shower. You're witnessing a chapter in the ongoing story of the solar system. A story that began 4.6 billion years ago and won't end for billions more. But this particular chapter, with these particular showers producing these particular displays, might only last a few more centuries or millennia. In cosmic terms, it's a blink. In human terms, it's your lifetime. The cycles are reliable for now. The showers predictable for now. But eternal is a word that doesn't quite apply. These are temporary phenomena, beautiful precisely because they're fleeting, significant because they're changing. And you get to watch them during this specific window of time, this brief moment when the Geminids are ascending, when Swift-Tuttle's orbit still brings its debris close to Earth, when 2003 EH1's ancient tail still crosses our path each January. If you do nothing else in 2025, if you only step outside once to watch meteors, choose the night carefully. Check the forecasts. Pick a dark location. Allow time for your eyes to adjust. Then lie back, face the sky, and wait. Be patient. Meteors arrive on their own schedule, not yours. You might see one immediately. You might wait 5 minutes. But when that streak of light appears, crossing the stars in less than a second, you'll understand why people have watched these showers for thousands of years. There's something profound in those moments, something that transcends science and data and predictions. It's the direct experience of cosmic motion, the visual proof that space is not empty, but filled with debris, that Earth is not isolated, but constantly encountering material from distant reaches of the solar system. Each meteor connects you, briefly, to processes that span millions of years and millions of kilometers. It's humbling, it's beautiful, and it's yours to witness, simply by looking up. If these explorations helped you understand meteor showers a bit better, if they deepened your appreciation for what you might see in 2025's night skies, consider subscribing to the channel. We're here regularly, exploring topics that blend science and wonder, that bring the cosmos a little closer while helping you drift toward rest. One curious soul at a time, we're building a community of people who find peace in cosmic perspectives, who look up and marvel at the universe around us. The meteors are out there now, even in daylight. Even as you read this, they're falling constantly, invisible against the bright sky, but still there, still burning up in the mesosphere, still adding their contribution to Earth's daily accumulation of cosmic dust. Tonight, when darkness falls, they'll become visible again, brief scratches of light across the fabric of night. And somewhere, someone will be watching, lying in the dark, waiting for the next streak, continuing a tradition as old as human wonder. The sky is vast, the showers are patient, and the universe, in its infinite complexity, offers these small gifts year after year, decade after decade, century after century. All we need to do is look up, be still, and watch the stars fall. Clear skies to you, and may 2025 bring countless meteor sightings, peaceful nights under dark skies, and a renewed sense of wonder at the beautiful, dynamic cosmos we call home. Sleep well, and dream of light streaking through darkness, ancient travelers completing their final, brilliant journey through Earth's sheltering atmosphere.